not seeing video yet.
Okay. So welcome to the first FunArc workshop on functional software architecture. The first speaker of the first session is one of the initiators of the workshop, Mike Sperber. I know him for quite some time, and he's not only trying, but also he's very successful at putting functional programming into industry for, I guess, 20 years or even more. So I'm looking forward to a really interesting talk. Thank you, Mike.
Okay, great. Got things covered up. Good morning. So, so welcome to the first workshop on functional software architecture, functional programming in the large. So this was an experiment I thought we'd try for reasons that I'll explain. Should we close the door? And I'm happy you're all here. First of all, I'd like to thank Graham Hutton, who unfortunately can't be here, my co-chair, who's ready to try this experiment. If you ever have a chance to work with Graham, please take it. So he's just a pleasure to work with and super organized. And also, I had the pleasure to work with this programming committee. I see Stefan is here, Simon is here, a whole bunch of other folks. And I've been on many program committees over the years, and this has by far been the most pleasant experience, I can honestly say. All differences got resolved unbelievably efficiently. And I think we put together a pretty good program. To put this event, and once we had the program together, the talks that we wanted to accept, there was one free slot, and that is this one. So I just decided I was going to fill it with, so now you can leave at any time. I'll put it like this. So this talk has not gone through peer review. But it might, maybe I can give you some context for this event. So I work for Active Group, and we've been doing software project development with functional programming in Germany for, I guess, 13 or 14 years now. We also run the leading German language blog on functional programming. We really do it across the board of programming languages. And also, we run the Bob Developer Conference. If you were there in Berlin for ICFP 2019, you might remember that there was a special edition of that. The next one is on March 15th in 2024. And if you're in Berlin for that, that'd be cool. Anyway, a couple of years ago, we had we had a small business teaching. Or we would give occasional courses to our clients on functional programming, but this was like 3 or 4 iterations that we did per year, and we were looking to improve our marketing for this. And so this was all about functional programming at the time. That was of course the thing that we were doing. And in order to make what we were doing more visible, we joined an organization called the ISAQB, which is a nonprofit based in Germany dedicated to the teaching of software architecture in general. And they have a whole collection of curricula on software architecture. I think there's 16 or 17. And we decided to submit another one on functional software architecture. This was a purely marketing idea at the time. And when we started working on it, we found out that, well, it sounded good at the time, but it occurred to us then that functional software architecture wasn't really a thing, right? If you kind of think about what has been published on how to do like large projects using functional programming, this is all scattered through our many ICFP papers, little aspects of it. Most books on functional programming are intro books, or they're kind of research books, but very little on how to actually do real industrial software projects in the large. And of course, that's what the software architecture community is concerned with. And so so we were thinking about that, and so the first thought we had to dedicate to what is software architecture and what is specific that we need to think about when we apply it, or when we try to apply functional programming to it. There's many definitions of this term, so I'm gonna say this, right? Software architecture is when you're dealing with large systems and long-lived systems, and of course, long-lived systems. I mean, they kind of have to be long-lived in order to become large. Surprisingly, many systems are long-lived, right? Even those that weren't intended to be that. And sort of the typical activities that software architecture is about. So first and foremost, most treatments on software architecture talk about splitting large pieces of software into building blocks somehow. And then there's a couple of sort of subordinate principles or activities. So you might think about, as you're doing programming in the large, how to meet the requirements that come from somewhere in the domain. It might be about improving the system's qualities, and it's about facilitating change. And I'll get to that in a moment. Maybe you're like me. You know, when I was reading this quality thing, I was thinking this is about making good software or bad software. But really, in the context of software architecture, people usually use the term quality to refer to this thing, to an ISO standard, ISO 25010, which is about the qualities of a software system. And so this is just a taxonomy of properties that a software system might have. And so on the left, you have some things, probably hard to read here, functional suitability, so they're kind of the functional properties, but then there's things like maintainability, portability, security, performance comes to mind. So there's all kinds of other properties that your software system might have beside its functionality that we might impact using software architecture. And it's worthwhile, I think a lot of the time, so if you're doing professional projects, you're concerned a lot with the functional requirements, and this is typically what you get from the clients, and all the other things often get forgotten. So if you're doing requirements, or if you're involved with requirements analysis in a realistic project, it makes sense to use a taxonomy such as this one. It's not a particularly good one, but such as this one. There are other ones. And kind of use it as a checklist to talk about with your client, is this important to you, is this important to you, is this important to you, and then have that guide your development process. Now, unfortunately, there's this, right? Here's the same ISO 25010 qualities, listed in sort of, by the time that they become apparent in a typical development process. So my colleague in the ISAQB, Markus Harrer, did a survey among software architects and requirements people and asked them, when does typically, this quality come into focus in the development process? And as I mentioned, typically what's first is, the functional aspects of software development. And then as you go down the list, the things further down the line are the ones that are less visible when you actually use the system, right? In particular, I want to focus for reasons that might seem obvious, but that really require explanation. So maintainability is pretty far down the list, right? And so I think we all know that if you think about maintainability late, you might have issues, right? And so why is that, though? Has anybody ever read this book? Seen this book? So you can only find it so this is old. This is like from the 70s. But this is, I think, one of the original sources of the word coupling, if you've ever heard, right? And so, and it's highly recommended reading because these folks, the authors, Ed Jordan and Larry Constantine, worked in software projects at the time. And of course, all the things that we think we know about software development were not generally known back then. They were really trying these things out for the first time. And they found out two things that are notable. First of all, when you look at the cost of a software project, right, that cost is not primarily what you spend until you ship first, until your first release. Instead, the cost comes up later as you change your system after that first release. So really the cost of software is approximately, so one way to think about it is the cost of software is the cost of change and not the cost of writing it from scratch. Right, and so that's one thing. And then they looked at, what kinds of software systems are amenable to change and which ones are not, right? And they found out that the software systems that are amenable to change have something that we now call low coupling. So they have fewer, as opposed to many, interdependencies between the different building blocks of the software, right? And so I think this becomes understandable if you really put yourself in the mindset of if you forget everything that you know, it's not immediately obvious that splitting your software into building blocks is a really good idea, right? It might be that, and I've certainly met practitioners who think, no, it's much better to put it all in one file and I can I've got everything together and so on. So what they found out that no, so the cost of change rises as you have higher coupling between the system's building blocks, okay? So and this is why, and this means that sort of this coupling issue is at the center of a lot of software architectural activities. So, but even in the 70s, people were thinking about how can we do that? How can we have low coupling? And kind of the father of a lot of things, David Parnas, has written classic papers on what we now know as software architecture. And the classic paper says that, well, the way that you should structure your building blocks is that a building block hides a difficult decision that you made in the design process. And this way, you can change that decision, right, because it's hidden by the building blocks interface, and that would be good. Now, strangely enough, this was 1972. Now, if you go to a bookstore and buy books, modern books on software architecture, right? So here's two prominent software architects, or there's Simon Brown and Uwe Friedrichsen, right? And when you ask them what their definition of software architecture is, they say, well, it's about making expensive decisions. So at that point, there's something wrong, right? So we were, in the 70s, we were thinking that really we should make decisions so that they're cheap, right? This is what this is about, right? But somehow, the architecture community has resigned itself to the realization that, oh no, we got to make expensive decisions early in the process, right? And if we get them wrong, that's a problem. So a lot of software architecture, strangely enough, is about making sort of upfront decisions these days, right? And so you might think, well, obviously, I mean, this is a world that's very, very different from sort of the way that I've grown up developing software, but I've been mostly at home in the functional community, which is really a almost completely disjoint community from that community. On the other hand, well, so we've all been doing functional programming. Yes?
I'm just trying to understand this idea of hiding the decisions.
Yeah.
So is it about putting you in a position where you can change your mind? So
Yes. Yeah.
Or is it about, okay, so it's not about delaying the decision as late as possible so you still have options?
I mean, I think I can use the same techniques to delay a lot of decisions, right? In practice. So anyway, so here, this is what we're thinking about, right? Design decisions. So anyway, so the paper, of course, goes into particular examples, that were relevant at the time. I think the simple way to think about this is, am I going to use like this database or that database? That tends to be an expensive decision, and I can tell you, in a software project, right? And so you build some kind of abstraction, some interface, right? And this kind of started the notion of having interfaces that would abstract over your database. But of course, what you can also do, once you're doing that, right? Once you're creating an interface to hide your database, if you're in practical software development, having to hook up your system, even if you've made your decision and hidden that decision by your module, you've still made it, right? You've still made that decision. This introduces all kinds of practical problems in the development process if you really have to spin up your Oracle instance to do any testing of your software, right? And so you might even not make that decision yet at all, what database to use, and instead put in some kind of, RAM-based, couple of functions that pretend to be the database. So I think it's both of these things, right? So anyway, so question for you, really. So I'm gonna put the work back in workshop today a little bit. So what have we done for architecture as a community? So it's an honest question, right? I have a list. I'm not going to tell you that list, though. So in particular, when it comes to splitting systems into building blocks, anybody have any idea? So here's an empty slide. Here's an empty slide that I could put things on. I could put things on that slide. What should I put on that slide? What have we functional programmers contributed to the art of splitting a system into building blocks? What would that even look like, a contribution?
Abstract data.
Abstraction?
Abstract data types.
I abstract data types. Very good. Okay, what else?
I mean, the ML workshop is just examples of
ML modules, so module system. So mechanisms. Modules in general. Very good. Okay. So we've provided. There's a whole thing there, right? So we've provided like technological mechanisms that help with expressing, you know, the splitting of your system into building blocks. Yes.
I think just abstraction in general.
Okay. Yeah.
I mean, it allows you to think of all the building blocks
Yeah.
in very
Okay.
ways.
Great. What else?
Polymorphism.
Polymorphism. Okay, the strongly typed programmer here.
Thinking about composition.
Composition. Okay, great. It's a great list. It's coming along.
Purity.
Huh?
Purity.
Purity. Okay. Okay, good. I'm just gonna.
So expressive type systems generally because the describe how to use a building block.
Yeah.
Have the component track that you
Yeah.
get rid.
Yeah. Okay. Very good.
Separation of concerns.
That is, of course, a general term in software architecture. What have we contributed to that? Actually, I don't even know what that means. So,
I think I was thinking about how you might have a functional core, and then so you might have a pure part, and then you sort of push all the complicated bits into a smaller bit.
okay, we'll get back to that, actually. So, okay, so great list. Which one of these things do you think has made it out of the functional programming community? Seriously?
Composition, that's not sure.
No? No? Tell you right now. So purity has made it out a little bit. We'll get to that. Yep, purity has made it out a little bit. Actually, that pure part versus the complicated bits, I'll get to that. So there's a shadow of that in the architecture community. I think that's it. That's it.
Inexpressive type system.
Yeah, so there you go. Anyway, so seriously, so I think, you know, we need to recognize that we have not made an impact, really significant impact on the architecture community, and that means also that that is what feeds into the developers at large.
I think type systems, expressive type systems is starting to penetrate compute like out of that world. So we're seeing it with TypeScript being very popular, or even Go.
Okay. Okay, yeah, so maybe even then polymorphism along with that, right? But as a, I think what we're not seeing is, I mean, we're seeing how that is entering programming practice, right? What we're not seeing so much is sort of enter the thinking of the architects, right? And so, but you know, I'll chalk it up as a win anyway. That we're, I mean, we got to grab onto whatever we have. Okay, so anyway, I might not just not. I don't think I have to go back to the full screen mode on this. So facilitate meeting requirements. What have we done there?
Not sure if this facilitates or adds extra burden on verified programs.
Program verification. Okay. Yes. Now that's sure made it out. Property-based testing. Is that from the functional community? I don't think so. That is depressing, right? But actually, I have good news on that one. But I'm sorry. Priority-based testing, well, to some degree, yes, to a small degree, right? Program verification, not really, right? I mean, most verification projects really already have like functional programmers or strong functional programming side to it, and it's very I'm trying right now to increase awareness, even that it exists outside of the functional community, and it is super hard, I can tell you. Okay. So maybe avionics might be an exception. Yeah. So I'll take that back. But these are very specific. I mean, these are very even within the architecture community. I can tell you that they're very isolated. It's a tiny niche, right? Anyway, but I have good news for you. So actually, there has been made an impact. I think a huge impact has been made by this book, How to Design Programs. So Matthias Felleisen's group, I think, started in the, no, I don't think, it started in the 90s to think about teaching programming as part of the intro course, and as a part of that developed a methodology for turning problem statements into programs, into systematic data definitions and functions. And this is huge. I think it's still pretty far from reaching its potential, but this is certainly an important contribution. And we're seeing, I mean, especially through the intro courses that are being taught in many places using that, we're slowly seeing that seep into the community at large. And and we're seeing actually some books here. So here's a book, Domain Modeling Made Functional, that does not come out of the functional community as such, but came out of the domain-driven design community applying functional programming. Also something else, combinator libraries, right? We kind of forgot about this one, which, here's 2001, and we can see the 2001, this was like folklore, right? Everybody was supposed to have known this in the functional community, and I think most of us know what it is. On the other hand, this is completely unknown out of the functional programming community, basically, combinators. Even though it could also be part of object-oriented programming, for example. There's no reason why it couldn't, but it isn't, right? Nobody knows about this. In part, I think, because there's very little documentation. We have lots of papers on saying, I made a combinator model for this, I made a combinator model for that, but very few on how they were built, what methods, what techniques were used in constructing them, right? If you think about it. So there's a fair amount. So here's my list, right? Design recipes, algebraic properties, so not far out from property-based testing, abstraction, combinator libraries, and from there also embedded DSLs. So these are things I think that are starting to make some inroads. So good morning. So next up, systematically improve the system's qualities. So as a reminder, here's the list of qualities. And this quality word plays like a prominent role in the way that architects talk about software that, I mean, to this day feels kind of alien to me. So here's a very popular book on software architecture by the SEI Institute at CMU. And they have this strange thing where it says, functionality does not determine architecture. And does that seem odd? So there you realize these people are doing something, I think, are in a different place than we are, right? So just to get you in the mind, so I think we've talked a little bit about sort of requirements. These things that we talked about were mostly about the functional requirements. But it does make sense to think about the other qualities a system might have in a more systematic manner. And what this community typically does is something called quality tactics. And so here's an excerpt from that same book where you go, well, if availability is among the requirements for your system, then here's a catalog of techniques that you might use in order to impact that particular quality, right? And so you can think of it like roughly like a patterns manual, even though the architecture people make like a big thing out of distinguishing this from patterns. What have we done? I actually have a list, I think.
Like affine types.
Affine types. Okay. Actually, so I have notes down here.
I'm still not quite sure what qualities we're talking about.
I mean, pick any one, right? So I'm sorry, they're hard to read. So there's performance efficiency. Then there is compatibility, usability, reliability, security, maintainability, and portability.
Okay, hang on. What does non-reputation mean? It's under security. I'm very curious about the meaning of this.
Let's not worry about the details here so much, because I mean we could talk all day about if that taxonomy makes any sense. So pick any one, right? Pick like performance efficiency, for example. Are there any functional techniques that we might bring to bear on a system's architecture in order to impact performance? user space scheduling. Is that a functional thing?
Like, hey, look, it came out of the PL research.
Okay, okay. Ah, okay.
Writing it to not have bugs in the first place.
Huh?
Writing it to not have bugs in the first place.
Yeah.
An idea that only functional programmers have ever had.
Yeah. So, I mean, certainly, arguably, there have been this research field. I mean, if we're thinking about security, right, there have been various works on type systems for various aspects of security, right? So maybe type systems for security would be one thing.
I would argue that they made this easier as well.
Huh?
The experience of refactoring with strong text systems versus not.
Refactoring type systems. Okay. I mean, generally, having equational reasoning for optimization, right, is something that we've been doing, right? Equational reasoning. Right, that's certainly something. Let's see, I have a list here. So here I was going to say that the module systems actually help with something that in this taxonomy is called portability. So they're just going to show up here again. And let's see, what else do I have? And generally we have things, I'm just going to put like a couple of dots here. I think we all, I think even we underestimate, at the beginning I said maintainability is something that is closely correlated with coupling, right? And I think even this community underestimates what effect purity has on coupling and what the big difference is between the software architecture community at large. So maybe I'm just going to say purity now, but other aspects, of course, might impact that as well. So I think the elephant in the room really is, what have we done for facilitating change? I mean, somebody already mentioned type systems for refactoring, right? Or static types for refactoring. Okay. I'm not, I would argue though, right, that sure we can think of cases where the types have made change harder, right? Yeah, definitely true. So as I was going to start with purity or immutable data, right? That would be one thing. And of course, again, sort of the functional module systems, like the one in the ML dialects, contributes to facilitating change. Anything else?
Gradual typing is important.
Okay.
Long before TypeScript.
Still, I'm just going to say, for the record, I'm still on the fence of that one, I think. So not sure about that. Anyway. So, but again, if you look at all of those lists and think, how many of these specifically functional things have made it out and are common practice in the software architecture community outside of functional programming, there's very little. For example, basically there aren't any module systems, right? There's no module, I mean, in use, right, in software projects. There's no module system in Java, for example, in the sense that we think about module system in ML, for example, right? Or even in Haskell, right? There just isn't. Which means that sort of the whole modules discussion moves to the level of objects and their interfaces, which is awkward in many ways. Anyway, so. But they don't get used as such, I can tell you. I think we might, I mean, no, but you're right. I mean, they've made it into Java. They have not made it into programming practice yet. So what we will probably see, they just arrived, so we'll probably see that happen. So that's good. Anyway, so making sure that we're finishing on time. So I think there's a couple of challenges, and I'm just going to give you, I think, about two challenges. One of them might be to think more about sort of functional macro architecture. What does that mean? Well, I mean, for example, the architecture community has come up with macro architectural patterns, organizational patterns for a software system as a whole. And the one that's most popular right now is something called hexagonal architecture. Show of hands, who's heard of that? Wow, nobody. So for the record, if you're watching at home, nobody raised their hands. So the good thing about hexagonal architecture, forget about the hexagon. It could be a circle or 8 corners. It doesn't matter. So the idea is very simple, that you put your domain logic in the middle of the system, and they talk about it in the idea is that you express your domain logic free of technology. So you don't introduce like the big frameworks that are common, like Spring or whatever, into the central realm of the application logic. And you move all interaction with the outside world to the fringes of the system. And you make sure that all outside interaction goes through interfaces, and I can replace the implementation of those interfaces specifically for testing purposes. So it's not a complicated idea, and it works extremely well in practice. People start their project because they can set up like a project template based on this. That makes it fairly easy to find your way around a project if you use this hexagonal architecture. Now, if the hexagon doesn't matter, you might think, well, wait a minute. I've seen something like this in the functional context, which is this pattern, right? And now this talks more about the technical side of things, right? That the pure stuff, right? This is not talking about the domain, that the pure stuff will live in the middle, and that your I/O monad is going to be at the edges of the system. But you can easily think about using this pattern at the typical facilities available in functional programming to implement the hexagonal architecture, right? And maybe you're not going to use objects and their interfaces to represent the interaction with the outside world. Instead, you might use effects, for example. So we found effects to be fairly effective there. But once again, I mean, one problem with this pattern is really that it only talks about the technical side, whereas software architects tend to think about the domain, right? And so there's a disconnect there. There's a mismatch. I mean, it might be particularly useful to also think a little bit about what's going on the inside here, because if you look at the architecture community, here's a recent blog post, and you can see here, well, a monolith means just a deployment monolith, right? It's something that you link together into one binary and you ship it, right? And you can see here, apparently in 2022, we still need to talk about modular architecture for monoliths. And down here, well, you can't see it. Well, if you look, no, you can't see it. Let's see if we can see it here. It's just outside. If you look down here, you can see that they've introduced a new term for modular monoliths called the modulith, meaning representing a very common consensus in the architecture community that your monolith is always unmodular, right? And that's kind of depressing, and it seems that we should be able to make a contribution there. So that's one thing, right, is that we could help the architecture community to build modular monoliths, maybe even like by default or something like that. So that would be one challenge. Another one would be to combine functional architecture with something called domain-driven design. So show of hands, who's heard of domain-driven design? Oh, at least about half the hands have gone up, so that's good. So for the rest of us, domain-driven design was started by this book, now I think having its 20th anniversary this year. By Eric Evans, which is about tackling complexity in software. And again, this is one of those books. You read it; it's very alien territory for functional programmers, and it takes a while. I'm still adjusting to sort of this way of thinking. But one way it does is so there's various parts of it. But one important part about it is that you split a system into sort of large building blocks, so that the individual building blocks can be worked on by separate teams. Okay, so when we're talking about for functional programming in the large really eventually means you have too many people, and you have to split them up into teams for various reasons. And then the question is, well, how do you do that in such a way that your development process works, right? And the reason for that is something called Conway's Law. Who's heard of that? Okay. About, again, half the people in the room, again, very familiar to software architects. So this goes back to a paper by not the Game of Life Conway, somebody called Mel Conway, who thinks about organization and organizational structure. And he said, well, any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. In other words, if you have 4 people and they work on a compiler, you'll get a 4-pass compiler. That's so programming language version that I'm sure you've heard, right? And it's very difficult to work against that. I don't recommend it, right? So really what you try to go with it. And so one of the central insights or one of the central ideas of domain-driven design is something called a bounded context. So the idea is that you split your system ruthlessly into parts, and each part can be worked on by a separate team. And then it might be that as you split your system, they might have things in common. So for example, if you split your typical e-commerce system, each subsystem might have its own, might need access to customer data, right? And the idea in the central idea in domain-driven design is you don't have a central data model for those things, even though those entities occur in several different bounded contexts. Instead, you allow the team working on each bounded context to develop their own models, right? And maybe you need to somehow correlate them, then you stick an ID in there, but really everybody does their own model. And that's a radical, I don't think I can convey how radical that idea is. And how effective it is in practice. So we have different models, the customer, which is also very different to sort of classical IT, where you have like a big relational database that has like the one customer table in the middle. So instead, everybody does their own, right? And sort of the logical continuation of this idea is an architectural pattern called self-contained systems, where, I'm sorry? Yeah?
How do you find some mismatch?
You don't.
Well, then you get lots of bugs.
Surprisingly, no. Not really. I mean, there are problems with this. I'll get to that in a minute, right? But you really, one way, a friend of mine who's headed a lot of groups doing this kind of architecture, he expressed it this way. He said, our programmers tend to be nerds that don't like talking to each other, so we're optimizing for that case, right? And the reason for that you're doing that, and this is maybe counterintuitive, so there have been studies on software quality in the sense of quality good or bad, and they found out, among other things, that high software quality correlates with a high release frequency. There you go. Not with lots of approval processes and code reviews and proofs, I don't know, that kind of thing. So the more signatures are required for release, the worse the software gets, right? And so what this does is it enables each team to release independently and therefore to have overall releases much more frequently. So the question of having does it create more or fewer bugs is kind of not the right question, because you have to have the trade-off not just between how fast do you create bugs, but also how fast can you ship fixes, right? And so it's a little bit more involved in that. Anyway, with self-contained systems, so that's that really is the extreme continuation of that idea. You only have each group, so each separate system maintains their own front end, their own business logic, and their own database, and their own DevOps. And the only communication between these subsystems happens via asynchronous feeds. So if somebody needs a customer database, they got to create their own, right? And if the customer data comes up in some other system, then you learn about it by just subscribing to that asynchronous feed and moving that into your own database. So again, in this talk, I can't really convey how extreme this idea is. So on the other hand, so domain-driven design, they've adopted functional programming, but it's a very different kind of functional programming than the one that we're used to, specifically because that group does not do abstraction, right? I don't really have time to go into that, so it just looks different. So really, the part of domain-driven design that's called tactical design is something completely different from the way that we do domain modeling and functional programming. It's evolved independently. It's got its own techniques. It's very different. And so really, there's a lot of work to be done. But I think this field would benefit a lot from functional modeling to create what I call deep domain models, which is typically what combinator models create, right? Is they create insights that weren't evident in the domain before. Also, one problem that these architectures have is, well, it's all well and good, you create this division into bounded context. You create this upfront because you have to assign your teams. And this is all fine, but all projects that I've talked to that do this end up with a situation where that boundary is in almost but not quite the right place. And then remember that all monoliths are unmodular. They don't know how to move the boundary, right? And that creates all kinds of problems. And so it seems like a very primitive, banal problem, prosaic problem, but if we could help that community move their boundaries, that would help. So I think we should think about functional macro-architectural patterns. We should popularize functional programming for architecture. We should truly integrate functional programming and domain-driven design, which is all the rage right now. So I'm wearing, I think, a t-shirt from last Domain-Driven Design Europe conference, and let me tell you, that conference is a lot bigger than this one. And that's just the European version, right? And write things up, and I guess some of you have done that for the proceedings, so thank you for that. There'll be more opportunities to write things up because there's an upcoming new category at JFP on functional software architecture. So if you deal with large-scale software in any way, or you think about it, right? Even if the thing that you did a couple of years ago could be framed into, how to do programming in the large, please think about writing it up and submitting it to JFP. And who knows, maybe we'll do another one of these workshops next year. That's it.
Thank you, Mike, for this very interesting talk. I'll have to look. There are actually currently no question from remote participants. If you have one, please write it on Discord. Well, are there any other questions here in the room? Yeah.
Could you take the mic so that the remote participants?
So something that I've observed from working in a sort of fairly large company, architecture-wise, is that an alternative to domain-driven design is a way where teams are empowered to make change across a large code base, even in parts of the code base where they don't own the code. And that works by having a very efficient code review system where you put up your change and then you can iterate on it with feedback from the people who are more familiar with the parts of the code that you're not directly involved with. I don't know. I wonder if you can comment on how that relates to domain-driven design. Is it different, or is it?
I think it's different. I've certainly seen organizations that succeed with this kind of model as well, somewhat to my surprise. I have to admit. So I mean, it's certainly not the only game in town. I don't think the DED people claim that it is, right? It's just one architect. So I wonder, though, that how much sort of organizational discipline is required to make sure that people don't destroy somebody else's code base. So how much culture? How much of that is culture, right?
A lot of automation helps.
Right. Okay. Yeah.
Lots of CI, lots of automated testing.
This, of course, helps with domain-driven design. Frequent releases as well, right? I should note, though, that maybe what you're describing, one advantage of that is presumably you really have a lot of testing that happens before releases still. And you have that in domain-driven design too, but with this kind of self-contained systems architecture, because the other teams release independently from yours, right? Some testing inevitably happens in production, right? And you kind of accept that, and you optimize for being able to fix your mistakes fast. Right? That makes any sense. Yep. So thanks. Yeah, good point.
More questions?
So you talked a lot about writing things up and sharing them, and you also talked about the way that signatures hamper releases, and that actually hampers software quality.
So we're not talking about type signatures, right?
Right. Approvals. We'll use that word. And I come from a highly regulated industry, and so there's a lot of tension between making sure that we're meeting the regulations we need to meet, but also being able to be more agile, be more technological, ship faster. And I want to highlight that I think what you've identified is that the problems here are as much social as they are technical, and there's not going to be a technical solution for a social problem. And so I wonder if you would comment any on that tension or how you see that progressing.
So definitely very relevant in that also the domain-driven design community sort of thinks about software from the social side rather than us functional programmers who tend to think from the technical side, right? And there's, similar to sort of types, static types or no typing, there's proponents, no, absolutely, the technical thing's completely unimportant, and vice versa, right? I mean, the choices that are made, in the social context are impacted by what is technologically and technically available to you, right? And so I don't think there's any way to separate those things. And in the highly regulated industries that I've worked in, yes, they were highly regulated. Yes, there were approval processes. No, these were not conducive to high quality. So I sometimes wish the social parts of these organizations would think about how to work with the regulatory processes in order to honestly think about achieving high quality rather than just making the process happy. If that makes any sense. Yeah, one more, and then we probably need to move on.
What is the largest project that you have worked on and designed?
I mean, I try not to design the whole project, right? So generally, I think the largest one that we've worked on is for a large retail chain in Germany. We've worked on their self-contained systems e-commerce system. So, and that had, I think, 5 or 6 teams with maybe 6 to 10 people each. Yeah, so
50 persons.
Yeah.
Developers.
Yeah, developers, and then you're also your product
QAs.
owners and so on. Probably in total about 100 people.
Great.
Yeah, so Simon's worked for larger, but still large enough. All right. So then let's move on to the next talk. Do I unplug or? So next talk's going to be remote.
Yeah, the next talk will be a remote talk.
I need my microphone.
It has been pre-recorded, so you only can ask questions in the end. It's about composable, representable, and executable machines.
Marco, can you hear us?
Oops.
I can't hear you, Marco. Well, the internet connection is not cooperating right now. Sorry.
Anyway, I can just play the video on my machine.
If you can, yeah.
Yep. Kill this.
Hello everyone, I'm Marco Perone, I'm from Italy, and today I'm here to present the paper Crème de la Crème, Composable, Representable, Executable Machines, which I wrote together with my friend George Karachelias. The paper is mostly about the journey that I did in several years of working as software developer throughout software architecture and domain modeling. And it talks mostly about how I would like to be able to design applications. And it draws a lot of ideas from the domain-driven design community and the functional programming community. And it all starts from a workshop called Event Storming, which is basically a brainstorming activity which you do together to explore a domain of a greenfield or a brownfield application. You basically gather a lot of people in a room. A lot of people, all the stakeholders in the domain that you want to explore. You gather them in the same room, you provide them with unlimited modeling space, basically a really big roll of paper or a white wall, and a lot of sticky notes. And you basically ask them to describe using these sticky notes the domain following a timeline. And as you can see in this picture, the sticky notes have different colors, and every color has different meaning. So this is a kind of a legenda which describes the role of the different colors throughout event storming. And the most important color and the most important sticky notes are probably the domain events, which represent the facts, the things that happen throughout the application, and especially things which are relevant for the domain expert. And usually when you do event storming, you start from them, you start from events. For example, an event could be an add-on was added to a card, payment was completed, and so on and so forth. And then you start asking, what's the origin of these events, of these facts which already happen in your application? And the answer lies usually in commands, which are triggered by some kind of user of your application. And commands represent the user intentions, their actions, their decisions. And for example, they could be something like add this item to the card, or process this payment, or ship this thing to this address, and so on and so forth. Another kind of sticky notes, which is the light brown down here, are called views, and they do represent the data needed by the user in order to make the decisions which they need to make to issue new commands. Then there are the yellow stickies, which represent aggregates, and the aggregates represent basically an aggregate of decisions. So aggregate represents decision which happens when a user triggers a command. So for example, a card could be responsible for deciding what happens, what really happens when a user requests to add a new item to the cart itself. Or a payment aggregate could be responsible to decide what happens when a user requests to process a new payment. Then there are policies, which are represented by the purple stickies, which represent the reactive logic that could take place after an event happen inside an application. And the keyword which defines basically a policy is the whenever word. Basically, whenever you have the word whenever in a sentence, you can represent that with a policy. So for example, whenever an order is completed, we need to tell the shipping domain to process the shipping, or whenever payment is completed, we need to notify the user with an email or something like that. And the last piece are the green stickies called projections, which are the part of the domain whose responsibility is to process events and to distill data which needs to be shown in the views. So basically, all the data of our application are stored in the events, and the projection just process them, filter the relevant data which needs to be shown to the user. And usually event storming is quite a chaotic process, but it usually creates a very nice representation of a domain. It's very nice experience to explore what a domain is. But another aspect of it that I really like is that it translates fairly easy into working software. So each one of these colored sticky notes, which I just described, could be turned into a specific component into a software architecture in an application. And there are actually in the domain-driven design community a lot of practitioners which do use this kind of approach to build complex applications. But the main issues that I always had with such an approach is that with event storming, you get to realize, to achieve, to build some kind of artifact which documents your domain. But it usually is something which is fairly disconnected from the implementation itself. So even though in the beginning, the implementation will follow closely what you have in your event storming, what emerged from the event storming, as soon as the implementation proceeds and time passes and new features are requested, the two things begins to diverge. So the event storming representation will remain still, will probably not evolve, and the code instead will evolve and will change. New commands will be added, new events, new aggregates, maybe new processes, new views, new projections. And so you basically arrive at the point where your initial representation is something like a stale documentation, is no more faithful to what the software is doing. And so one thought which remained with me for a long time was how to solve this mismatch, how to fill this gap between these two aspects, the documentation you basically get from storming and the implementation itself. And the first step to try to answer this question is to look exactly at this diagram and realize that even more than software architecture, this really tells about the role of the things which are involved here. So if you look at commands, which are the blue ones, events, which are the orange ones, and views, which are the light brown here, as data and aggregates, policies, and projections as processes, you can see that this diagram here is describing the domain of an application just as the composition of some processes. And if you think a little more about that, you realize that these processes are almost pure. They mostly need to have a state. Actually, projection, they are usually pure. Aggregates needs to have some state involved, so they are just purely stateful process. And policies, they usually have other side effects, but mainly they also are stateful processes. So stateful processes play a significant role in this architecture. The architecture is basically a composition of stateful processes. So talking of stateful processes, one common way of implementing stateful processes is using Mealy machines. A Mealy machine is a finite state machine whose output values are completely determined by the current state of the machine and the current input. And I always like the concept of a Mealy machine because it has, in my opinion, three really nice perks. So the first is that it has a really simple model, which is basically described by this record here. So it has a state, which here I call initial state, and an action, which is basically a function which, given an input, it can produce an output also depending on state, and you also have the ability to update the state. So it's basically a stateful computation which consumes an input and produces an output. Then another perk is that a state machine allows, a Mealy machine in particular, allows a graphical representation. And this is extremely nice when you want to document and to represent things. So for example, a graphical representation that you could use for a Mealy machine is this one, where the circles represent the possible states of your machine and the arrows represent the available transitions, where the numbers above the arrows, they do represent the inputs and the outputs of the machine. So for example, if we are in state S1 and we receive an input 0, then we move to state S2 and we emit an output of 1. We can even simplify this graphical representation, basically forgetting about inputs and outputs and preserving only the state transition. And we can get something like this. So this is basically the graph of the available transitions for a Mealy machine. And the third perk for Mealy machines is that they are extremely compositional, meaning that you can take two Mealy machines and compose them to obtain a third Mealy machine in several different ways. So for example, you can take two Mealy machines, one consuming inputs of type A and producing outputs of type B, and another one consuming inputs of type B and producing outputs of type C. And you can combine them to obtain a third Mealy machine, which just consumes inputs of type A's, uses the two Mealy machines in sequence, and then produces outputs of type C. Or if you have two Mealy machines, one from A to B and the other from C to D, you can compose them to basically run in parallel. So if you're able to provide to them an inputs for each one of them, so basically a pair of inputs, you can run both of the state machine, providing to each one of them their the input of the correct type. And then you can collect the outputs and basically output them in a pair. And so you can compose the two inner machines and obtain a bigger machine, which is basically the parallel composition of the two. And also, if you have the same two machines, one going from A to B and the other from C to D, you can compose them in another way. So, for example, if you provide as input an either AC, so something which is either an A or a C, then depending on what you have as input, you can either trigger the above machine if you have an A, or if you have a C, you can use the machine below. And in the end, you will get as output either a B or a D, depending on the input that you had. And there are actually more ways you can compose Mealy machines, but this is just to give you an idea that they are extremely compositional and they allow to build complex machines out of simple ones. So if now we agree, and at least I do agree with this, that Mealy machines are a nice way to implement stateful processes, the next question is, how do we encode a machine? So what's the concrete implementation for a Mealy machine? So if we look in the Haskell literature, basically we can find a package called machines where we find this data type. So the Mealy data type is a new type around a function which consumes A's and produces B's, and a new version for the machine itself. So basically, when you provide an input, you get out an output and a new version for the machine, which you can then use to consume future inputs. This data type is very nice and simple to use and understand, and it's also extremely compositional. For example, with it, you can have instances for the category type class, for the arrow type class, and for many type classes from the profunctor hierarchy. But this data type falls short when we want to obtain a graphical representation out of it. This is because what we have here is a function, and the only thing which we can do with a function is run it. We cannot extract any kind of insight about what the function itself, about the logic of the function itself. So we cannot generate some documentation, we cannot generate a graphical representation, we cannot somehow enforce that certain invariants are enforced in the execution of the function itself. And if we want to try to achieve these things, mostly the graphical representation is something that we would really like to get. What we could do is basically to add some more information to this data type. And the information that we would like to add is basically the collection of available transitions. So the transition which can fire during the whole life of the state machine, which is basically a directed graph, and we can just store all the nodes basically in this graph in a list and have what I call the topology, which is, as I'm saying, the directed graph of the allowed transition of the machine. Once we have this information, we can decide where to store this information. So we could store this at the value level alongside as the running function for the state machine, but this has still some kind of an issue because there will still remain some kind of a gap between what's described in the topology. So in the topology, we will say we can perform these transitions and the implementation itself of the running function of the state machines, where maybe we are actually performing a state transition which is not in this list. So this could be enforced manually, or maybe it could be enforced through runtime validation. So every time we want to fire a transition, we will need to check if that transition is actually present in the topology or not. And if not, we will need to do some kind of error handling procedure. We could also have another option, which is basically storing the topology at the type level. If we do so, and we create a data type like the one that I'm showing you right now, where we have the topology at the type level, we can use the topology for several different things. So we can use the topology to actually generate graphical representation for the implemented machine. And we can also use the same topology to make sure that the implementation of the machine is only firing allowed transition. And we can do that at compile time. So we're absolutely sure that when we run the machine, only transition present in the topology could be fired. Still, doing such a thing creates a little bit of an issue with respect to compositionality. And the issues are actually two. The first one is mostly technical, because now we have three type variables in our data type, which are the topology, the inputs, and the outputs. And having three type variables, we cannot have instances for all the type classes which relate with compositionality. So we cannot implement an instance for category, not for arrow, not for profunctor, and so on and so forth. And the second issue is that once we have the topology at the type level, and we try to compose two machines with that type, we are forced to compute the topology of the resulting machine at the type level. Well, that's not impossible to do. It's still hard. So it's not that we are completely losing compositionality. We can compose machines, but it becomes hard pretty quickly. So potential solution to this issue is to basically somehow forget in our main data type about the topology, and introducing a new data type, which I call the state machine here, where we have as type variables only the input and the output. So solving the issue that we had when we had three type variables there. And basically create a free structure over the previous data type, which I showed you. And so we will have basically the basic data type, which would enable us to create the leaves of an abstract syntax tree. And to create this basic state machine, we will need to provide a state machine, a Mealy machine of the previous data type. So a state machine which knows about its topology. And then we could use the other constructors to represent the composition operation that we might have. So for example, we could have a separate constructor for sequential composition, another one for parallel, one other for alternative, and so on and so forth. And doing so, what we get is basically an abstract syntax tree of compositions of Mealy machines, where the leaves are Mealy machines aware of their topologies, and the other nodes are just describing how to compose the subtrees. So for example, machine 1, machine 2, machine 3, and machine 4 in this diagram are all machines which are aware of their topology. And then the parallel, alternative, and sequential boxes that you see there just describe how we need to compose their subtrees. So for example, machine 1 and machine 2 needs to be run in parallel. Machine 3 and machine 4 needs to be composed sequentially. And then we need to execute in alternative the result of the first subtree and the second subtree. And once we have this abstract synthesis tree to actually use it, we need to interpret it. And we could actually interpret this in several different ways. The two main ways are, well, actually for running a tree of machines and for creating a graphical representation. So when we want to run, basically we need to say how to run the leaves. And then, given the knowledge of how to run the subtrees, how to run, for example, a parallel box, on how to run an alternative box. So knowing how to run machine 1 and how to run machine 2, we can say that, well, if we want to run them in parallel, just run them both and collect the outputs. Or if we want to run machine 3 and machine 4 in sequentially, as we are saying here, well, first run machine 3, then run machine 4, providing as input to machine 4 the output obtained from machine 3, and so on and so forth. Something similar could be done with a graphical representation. So we need to say how to create a graphical representation of the leaves, but since the leaves are aware of their topology, we can use their topology to create a graphical representation. And then we need to say how to create a graphical representation, for example, of the parallel composition of two machines, given that we know the graphical representation of the two machines. And we actually have different ways of doing this operation. We can basically create the state graph of the composite machine, or we can use this basically to represent basically really in parallel, showing two boxes, one on side of the other, showing that these two machines will need to be operated in parallel. And so at this point, with this data structure, what we achieve is we were able to use the simple model provided by Mealy machines, even if we add this topology concept to it. But I would argue that it does not complicate too much things. We were able to get a graphical representation of our machines, and we still have the ability to compose them as much as we want in several different ways. So basically we were able to achieve all the perks that Mealy machines offer in one single data type. All these ideas which I just talked about are implemented in a library called CREM. And at this point, I would like to show you basically how you use CREM. So basically, I would like to show you CREM from the user's point of view. So suppose now, just for the sake of the example, that we want to implement a checkout procedure of some kind of an e-commerce. So basically, we receive a request to process payment, and we need to process it. And maybe at the end notify someone else that the payment has been completed correctly. And so we want to implement it using the architecture which I described in the beginning. And we will start trying. So we will need to have to implement 3 state machines, an aggregate, a policy, and a projections. So let's start from the aggregate, which is the one which basically decides what to do when a user emits a command. It decides what really needs to happen in the application, emitting some events which describe what really happened. And so for the sake of the example, we will have two commands. One will say pay the card, and the other will say mark the card as paid. And two events, one called initiated will say, okay, the payment procedure just started, and the other completed will say, well, everything went smoothly and we're done with the payment. And to implement the state machines which describe the aggregate will, as the first step, we need to define the topology. And to define the topology, we need to define the vertices of the directed graph of the available transition of our state machines. And actually, we'll have three vertices: waiting, which is the initial state before everything starts, initiating, and complete. And then the topology itself is saying that if we are in a waiting state, we can only go to initiating. If we are in an initiating state, we can only go to complete. And if we are incomplete, we can go nowhere else. So we cannot go back to waiting and initiate. And at this point, we need to define an intermediate state type, which in this case is basically isomorphic to the vertex type, but in more complex cases allows basically to store more data inside a single vertex of the topology graph. And once you have defined this data type, you can really start to implement the state machine. And to define the state machine, you need to define the initial state, which will be waiting state, and then you need to.
If the picture is blank out. There we go. Thank you.
Form the action. And to define the action, you say, okay, when we are in the waiting state and we receive the pay card command, we're gonna emit the initiated event and we are gonna go to the initiating state. Or, for example, when we are initiating state and we receive the mark card as paid command, we will emit the completed event and we will go to the complete state. In every other case, we just do not modify the state and we do not emit any event. And then we need just to wrap our, we basically need to lift our topology aware machine, which is the leaf of our tree, to the state machine data type. After that, we have the policy, which is basically a payment gateway, which is that part of the application which reacts to the events to request new commands to be executed. And in this case, what happens here is extremely simple, maybe too simple. What we're saying here, every time we receive an initiated event, so saying that the payment procedure just started, we will ask the application to mark the card as paid. So basically saying that every payment will go through smoothly. Usually this is the policies where you interact with external systems. So in reality, this would be something which would call an external, probably payment gateway, which will return you some result, which will you use to trigger the mark as paid command, or maybe do something else. And in the end, you have the projection, which is just going basically to project to the user the data contained in the events. In this case, what we want to tell the user is whether the payment is in the initial state or in the final state. And also this is basically a pure function saying that when we receive the initiated event, we go to the initial card view value, and when we receive the completed event, we go to the final state. And at this point, we implemented our aggregate, our policy, and our projection. And what we need to do is basically compose the three of them to get the representation of the whole domain of the application. And the application is nothing else than another state machine, which is obtained just by composing the three state machines that we already have. So first, we composed the card and the payment gateway, so the aggregate and the policy, in a feedback loop, basically saying every event will trigger the policy, which will create new commands, which will trigger the aggregate, which will create new events, which will trigger the policy, and so on and so forth, basically in an infinite cycle. And this will be basically the right model of our application, and then we can compose this together with our projection, which is payment status here, to create basically the whole application that we have. And as soon as we have that, we can use the functions provided to us by the CRAM library to generate a graphical representation of our domain. And what you can see here is that our three boxes, one for the card aggregate, one for the payment gateway, and one for the payment status projection, each one of them containing the possible state transitions that can happen inside that state machine. So a card is the only one which has a non-trivial topology. The other two are just have one single state. And then you have the arrows connecting the boxes, representing how the state machine are connected. So if you remember, card and payment gateway were connected in a feedback loop. So you see the two arrows going back and forth between the two machines. And then card and payment status were basically connected some kind of sequentially. So first we do card and payment gateway, and then we perform with their output, we perform the payment status. Basically that's all I got for you today. The paper is already online on the ACM digital library, and if you want to take a look at the code and more examples, you can just go to the repository of the CRAM library. And if you have questions or any kind of feedback, I'm extremely glad to receive it. Anywhere you can find me on the web, you got here my email and my blog and my Twitter account, my Mastodon account. And I'll also be happy to answer some questions live now.
Yeah, thank you, Marco. I don't know if you are hearing us, because I think there are some problems with Zoom, right?
Yeah.
So I don't know how we could handle questions. I mean, could we make a Zoom session directly with Marco through your laptop mic, maybe?
That might be best.
That,
Try.
that comes to my mind. Otherwise, we could relay questions over Discord, but that seems to be a bit complicated.
For a moment. Oh no. Go for it.
Do is log in, and then you receive your second factor via email.
So let's see. Got it. And there's Marco.
Okay.
Okay. Marco, can you hear us? We need to unmute and video. Marco, can you hear us?
Yes, I can hear you. Can
Yes.
you hear me?
Oh, great.
So, well, you wouldn't believe we've got a complicated technological setup here, but do we have questions?
Yeah.
Yeah.
Any questions? Ask them now. I don't know if Marco can.
Yes.
Yeah. Okay. Any questions?
Should we go up to the laptop?
I don't. Maybe yes. Maybe.
Yes.
Okay. Great.
Hi, this is Will Creighton. So I'm curious how this framework relates to the event storming process you described at the beginning. In particular, are you imagining that basically if you went through event storming, your idea for the CREM framework is you would immediately go and take those sticky notes, encode them into your Haskell framework, and then is that intended as like a model that would co-evolve with your implementation, or is the idea that if your code base is also in Haskell and everything is just normal Haskell code, that would serve as the template that would then get sort of maintained as you go?
So the idea is to have the code base in Haskell, at least because I'm using some fairly complicated bits of the type system in Haskell to implement CREM. So yes, you would take basically the output of the event storming session, you would translate that into data type and state machines. And then as you go, as you modify those data types and those state machines, you would be able to generate the graphical representation, which is not exactly the same thing as the event storming because, I mean, the representation is different, but you would still have some kind of a dual vision on the implementation and on the documentation, which go along together. So there's no more a gap between your documentation when you had the event storming session and your real implementation.
Okay, thanks.
Questions? Just come to the front. I don't think you have to use the mic because
Oh, I should. Hey Marco, thanks for that presentation. So I have a quick question about handling transactions and stuff like item potency, because I think the biggest disconnect happens whenever it does happen is when you go from, you know, this exercise of event storming to implementing a real application, and you have to handle things like, you know, either compensating events or transactions, whatever you want to call them, stuff like item potency, etc. And that seems to be always the hang up in the model that you came up with and the, you know, and the real implementation, and things get super hairy. So how is that, how do you model that in this framework, and eventually how is it implemented?
So from my point of view, this is somehow independent from how you implement stuff. So it's somehow independent of the usage of CREM or any other technology. So it's more of a kind of a business problem or a domain problem. So what do you do when something fails? I mean, it's not just a technical problem, but it's also a domain problem. So first you need to talk to the domain expert and understand how to deal with those aspects. So is that operation really important? So you probably need to have an event for that. And if you do have an event for that, then you have basically a value in your application, and you could react to that maybe with a policy, maybe with something else. So I would mostly think that is something more related with the business logic. So really the business aspects of how you implement the domain more than with technical ones.
Okay. Yeah, thank you. I also have a quick question. Are there any real-world projects, applications, whatever, that have been realized with this approach, with your library?
Sorry, I missed basically all of the question.
Okay.
Can you repeat that, please?
Are you hearing me now?
Yes, now I'm hearing you.
Are there any applications that you have realized with your approach? Or parts of application, whatever?
Well, I have some, basically, to be sincere, I have some examples, but they're mostly toy examples, so I don't have I never had the time to build a real production level application with this approach. I don't have doubts that it could work, but I never went into the nitty-gritty details of integrating this into a real production system.
Okay, thank you. Thanks, Mark, again.
Thank you.
And now we'll have a break until 11, and then we meet here again. Okay. Thanks, Marco.
Thank you all.
So, I do remote talks when you want to Zoom. Okay.
It's good to have you all here. The room is packed, which is mostly a property of the room, but it's still great to have you all here. Our next speaker is Ben, who told me that most important to know about him is that he goes by Ben and not by David. So even though the name tags are something else, but at least you don't have Microsoft as a name tag, so that's
right.
Better than some people. Bogdan, his co-author, is in Romania. I don't know if he's listening, but thanks for your work. And I heard there are some board games in the talk, which I think makes the talk already one of the best ones in the whole week. So go ahead.
Thanks. So yeah, the audience got a little bit of a preview. We're going to talk about functional shell, reusable components, easier GUIs, and just a skosh of Frosthaven. So I'll dive right in. We like to build small GUI tools, or at least I have discovered that I enjoy this now. And we're going to do this with Racket. So if you're not familiar, Racket's a Lisp. It specializes in language-oriented programming. It's got one of the best macro facilities out there at all, but also has lots of other. And the typical solution with most languages, but especially with Racket, is the object-oriented toolkit. And I want to stop and say there's a lot of really good things in there. It's cross-platform. It has a wonderful plethora of widgets. It's actually used to build the Dr. Racket IDE, which is a phenomenal both teaching and professional tool. But there are some downsides. Working with this toolkit, we have lots of classes, and our code is not really organized in the same way as our application is. We have to do a lot of state synchronization between our application and the things we want to display on the screen. And in general, we struggle with composition, reuse, abstraction, all the things we were talking about this morning with Michael. And it's a bit daunting. So it really feels like you need expertise in the widget library to start. You got to know not just what a button does, but what a canvas is and a drawing context and all of these pieces. So we found that experts like Bogdan, but also complete novices like myself, struggle to write large programs with these toolkits. So we're not so happy. But on the flip side, working with GUI Easy, Bogdan's library has been a joy. Our GUI containers are going to programmatically contain their children, so we'll see some examples of what that means in a moment, but that sort of solves our organizational problem. We get these automatic updates via observables, which sounds like one of the Gang of 4 patterns and is somewhat related. So that solves our state synchronization problem, and we get composable functions that actually represent our graphical applications. So all the good functional programming stuff that we know and love, we have functions, so we get to do all of those things. And then because it's got such a small core and it's easy to extend, you don't have to have quite so much expertise in the library of widgets. But for those that need those expert capabilities or that want to tap back into the expert system, there's some escape hatches that kind of bring you back down a level, and I'll talk about those towards the end. So the sort of high-level version is GUI Easy is much easier to learn. It's also been a gateway to the object-oriented toolkit. So I've actually started using the object toolkit more because I'm using GUI Easy in my projects. So we're much happier with our solution, which really revolves around these two fundamental concepts of views and observables. Before I cover too many of the details, I want to do a small example, and by small, this is our goal, right? So this is where the board games come in. Frosthaven has area of effects, and it's important, especially when you're talking about what the monsters are doing or what the characters are doing, to really be able to describe those pictorially. For the game, we put in lots of data about how these things work. So on the left, we're going to have an editor. We're going to type some textual representation of that area of effect. And on the right, we want to get a live picture, some feedback on what that's going to look like when we render it in the game. This is, and it's very dense, so just bear with me. This is typical object-oriented Racket code for the kind of editor that we want to build. But I'm going to walk you through the key components. This is all of the main functionality of that application, okay? This bottom bit down here is drawing the picture with a little bit of error handling. We have some style on our editor. We have our state for our editor input at the very top, and we have just a label for the window so that we know what we're dealing with. We have a little bit of input synchronization, and we have to be careful that we get the editor input and refresh our canvas so that we draw an updated picture. Otherwise, our picture is stale. And then the rest is pretty well boilerplate. We have names for variables that we never use. We have to construct these widgets with references to parents, which sort of is going to tie back into our organizational problems. And as a whole, the picture is sort of scattered about. We have the functionality, but we also have all this other cruft. But it works, and so here's, if it will animate. So you can type, and you get these nice pictures, and that's roughly what they look like on the cards in Frosthaven. So it works, but we think we can do better. And in particular, we think we can make it easier to write these sorts of small utilities. So here's the GUI easy code. We want to render something to the screen, so we're just going to start with a function call, render. What are we going to render? It's going to be a window. Okay, it has a title. We need to do a little geometry management, just like in the previous version. So we want to have something on the left, something on the right. It's going to be a horizontal panel. And the first child of our horizontal panel is the input widget. So this is how we get textual input. And we need some state at the very top. That'll be our input. And then when the input changes, we'll update our input to say, hey, there's been some user input. Our other child, though, is a picture canvas. And all it knows how to do is draw a picture in response to some data changing. That data is going to be our input state. And when it changes, we'll apply this function to produce a picture and automatically draw it. That's the whole code. Much less dense. Or much less boilerplate, far denser in concepts. We have exactly what we need, but you're also seeing the sort of functional style of constructing things. And this works exactly the same. I've embedded it in the slides here, so we can type, a picture out, and it works, right? It works just the same, with the major difference being the code, the organization, the architecture of how we build the system. Any questions so far? Stop me if you get lost. So I said the primary concepts are views and observables. Let's talk about observables first, because that's what we saw when we talked about state management and reactive updates. Observables are values. We have a constructor. We typically use the @sigil here for that. And we have a couple of major operations. We can set the observable from some value v to some expression e. We'll evaluate it and get a new value in. And any listeners that are waiting for changes to the observable are going to get notified that that value has changed. We can also update observables by applying functions. So a more typical version is that with our left arrow here, we're going to have, instead of @v, we'll have @f of v. In the other direction, we're going to map observables into new observables. So the left arrow is a state change, and the right arrow is produce me a new observable in a different domain that changes whenever v changes, but the observable's value is f of v instead of v. And then at the slightly lower level, we can extract v out of the observable, and we can subscribe to events on that observable when that's useful. Views, however, take care of most of the subscription details for us. Views are functions, and in Racket syntax, this means that they return an instance of the view interface, but we'll talk about that a little later. In particular, though, views are observable aware. So we take in our dependencies, like some data and how to turn that data into a picture, and views will react to changes in those dependencies. Views are also composable functions. So we saw the hPanel example earlier. These children are going to be themselves views, and we're going to compose that into a larger view, and we can sort of take that to the extreme. Here's a very simple example out of things like 7 GUI. We have a counter. We have a window that has 2 buttons and some text, and the counter operates, just to show you. The way we're doing this is the 2 buttons have callbacks attached that say subtract 1 or add 1 from the value. And then the really interesting bit is the text widget in the middle that actually displays the counter value. The counter value is a number, but we're able to map that into a string, and our text widget updates with the string value whenever our buttons update the actual count state. Any questions about this example? Because we're going to take it apart in a minute. So like I said, we're going to take it apart. We're going to abstract a little. We can take that H panel with its couple of buttons and some text, and we can call that a counter view, right? We can turn it into a function because, after all, views are functions. We need some dependencies. We need to know what the count is. And we're actually going to turn that direct update into a callback, and we're going to call it action here. And that gives us the ability to render multiple independent counters and have reusable abstractions. I'll spend some more time talking about this action callback and why it's important. The idea here is to reduce coupling and to really give us the flexibility to decide, when I create a counter view, how should it react to user input? It's going to tell me that users have clicked buttons or done some other action, and I get to decide, as the constructor of counters, what happens. I don't have to have counter make that decision for me. So that gives me flexibility, and it also reduces the coupling between a counter must behave in a specific way and gives me more flexibility about what that actually means.
So at this point, how would you describe in your manual or API this counter abstraction?
So, and that's a good question, because the project that I have been working on for the last little while has its own library of domain-specific abstractions and their documentation. So a description for something like this counter might say, inputs are a count variable, which needs to be an observable of an integer, or some kind of number, and an action callback. I would tell you that action callback is going to be called with one of two values, right? In a typed language, you might have an enumeration for those kinds of values. And I'd say you're either going to get a procedure like subtract one or a procedure like add one, which takes a number, turns it into another number, and it's up to you to decide what to do with that procedure. In our case down here, we're actually updating the counter variables. So we're saying that when we get a procedure like add one or subtract one, we're going to update the corresponding counter variable by applying that procedure to it. So we haven't functionally changed our actual example, but you could imagine doing something different. In fact, if you swapped these two counters, then the buttons would operate on the other counter, right? So you have that flexibility. Does that help answer the question? Okay. The important piece here is that we're able to create domain-specific concepts from the lower-level graphical concepts like buttons. There's some relationship here, I think, somewhat obviously to the model view controller frameworks. In particular, we have some state, it's a model, and we have some views, they are views. And then the most nuanced piece, the controller, and how these callbacks work. As I said, they give us flexibility. One of the major criticisms of MVC frameworks for the last several decades, I think, is that controllers and views tend to be very tightly coupled. And here we're sort of loosening that by a large margin and saying that we should pass data around and not force you into a specific way of acting. The style of application that this tends to look like, we're going to have observable state at the top levels of our abstractions, and we're going to feed bits and pieces of that down to the child and leave components that are really responsible for ultimate display. But we're going to have our controller callbacks react to user input at the leaves and feed that back up to the top level to really decide how to make decisions. This came a little bit out of the Elixir community, which I think popularized the phrase data down actions up. And so that's what we're seeing here. We have observable data that comes down the application and actions that come up the application. I also like to think of reusable components as being somewhat isomorphic to pure functions. We take in data, we take in all the data we need, we take in the callbacks that we need, and we don't interact with the outside world. We don't directly mutate our inputs. Instead, we delegate that responsibility to the top of the application that knows how to mutate appropriately. That would be kind of a functional core imperative shell. There are some other details in the paper. We talk about the object lifecycle and how the view interface and renderer objects really make this more of a framework than just a toolkit. The central concept there is inversion control. GUI Easy manages the details of what a graphical application lifecycle is like, and your job is put the boxes together, put the puzzle pieces together. One of my favorite bits is that we talk about black box versus white box frameworks. And so in this discussion, a white box framework is very transparent. So you need to know all the details in order to be able to put the pieces together. Whereas a black box framework hides a lot of details from you, but the trade-off there is that those pieces are much easier to put together and glue together. In that framework, we like to think of Racket's GUI framework as being white box, being very object-oriented, and GUI Easy being more black box. But we have these escape hatches. You can create custom views, and you can use Racket's mix-ins to tap back into that expert system level and get the functionality you need. We use this to great effect in Frosthaven and in other projects. There's a plethora of related work that we talk about in the paper, other GUI toolkits, but also you might be thinking of React.js and other reactive web frameworks, the functional reactive programming community that's been looking at ideas like this for many years. And there are definitely some correlation here. I think what's somewhat unique about our work is the packaging and the way we're applying this directly to graphical systems and giving you control over the full stack. Conclusion, I just want to wrap up, and then if we have time for some extra bits, I'll go through them. GUIs with objects tends to be a little more difficult. It's more of an expert system. GUIs with observables and functions, it's easier. We get all the benefits out of functional programming that we're excited about for functional programming, like purity, composition, abstraction, reuse. And we started asking ourselves what other imperative or object-based systems deserve this FP facelift, this veneer of functional programming on top of it that allow us to get these benefits from imperative systems. So that's what I have. I have plenty of extras to dive a little more deeply into some details if people are interested, but that's it for me.
Thanks, that was great. We have good time for questions, and I see the first hands are raised, so yeah, I guess I'll just...
Thank you. Hi, Will Creighton from Brown. Can you go back to a slide that contains one of the code snippets on it?
Certainly. Here, well, let's do one of the counters. That's a simpler example. So this was one of the early counters.
Okay, so you know, a really critical thing in stuff like React.js, when you use frameworks like MobX or Solid.js, is you need to localize state in the sense of, if I change one piece of state in a tiny part of my GUI, I do not want everything to re-render.
Right.
Or even if I'm using some kind of shadow DOM, I don't want all of that code to get invoked and then do a bunch of useless comparisons. And it's not obvious to me here, just looking at this, if I change count, how do I only know that the text should update as opposed to everything else, without doing some kind of dependency analysis that presumably is not exposed at the sort of library level. So is there any consideration for that performance issue, or how you would deal with that in this style of framework?
Yeah, so let me just rephrase and make sure I understood. I think the central question is, right, what's the level of dependency analysis here that helps us with performance trade-offs, like re-rendering the whole tree of the application versus just the subcomponent? Is that right? Okay. So this is where I'm going to go back to views are functions, and especially views are mostly pure functions. They create a representation of the graphical object, which means that the rest of this tree doesn't even know that text depends on count, at least in this presentation of the code. So hPanel and button have no idea about count, except that there's, so I'm glad I brought the extras. The way this really works is that our representation tells containers about dependencies, and containers forward updates down to widgets. But my widget has to selectively say, I'm interested in this dependency, and when it changes, I need to make X change. So the picked canvas doesn't even listen for updates to the counter or whatever other variables are involved. So they're not making any changes, but it's a decision that's made based on, here's the dependency that's changed, and you decide as a view, is that something that you're interested in or not?
Sorry, how does picked canvas know not to listen to those updates?
Well, picked canvas isn't even, so let me go back to the picked canvas example, which is here. Picked canvas, well, that's a bad example, okay. So
but I'm interested in this example, though.
yeah, so in this case, right, pick canvas is interested in input. Okay. So it must know that it's that input is a dependency. So when you construct a pick canvas, you're giving it the input observable, and it says, okay, that's an observable.
Yeah.
I must be interested in its changes.
Yeah.
But in the counter example here, right, button has no knowledge of the count variable, so it can't even express an interest in that dependency.
But how? But like text, I assume the implementation of the text widget cannot introspect the expression on the right and know that it refers to @count.
Correct.
So how does
it's an anonymous observable in that sense. There's
okay. I'll move on. I'll let someone else ask a question. But I think
let's
details
talk
here
later.
I'm
I think Bogdan has a better answer for you than I do.
Okay, thanks.
So I, once upon a time, wrote some very simple graphical things using Big Bang, which is the Racket kind of event loop for students. And I'm trying to think how I would talk about the architecture of GUI Easy versus the architecture of Big Bang versus the architecture of the object-oriented toolkit. And this, if I put on sort of my simple-minded hat, I'm looking at GUIs, oh, this is a nice compositional way to write Big Bang functions. But I don't know if that's a good way to think about it. So could you say a little bit about how would you describe I don't know how well you know, you might not know Big Bang, which is okay, but how would you describe how these things are put together? What is the architecture of the system? How do they think about functions? How do they think about objects or not objects?
So the good news is we have a Racket expert in the room. I'm not as familiar with Big Bang, but my understanding with Big Bang is that it's a lot like our state machines that we were looking at earlier, right? We have a state and some functions that manipulate it and know how to draw pictures, right? And it's pure function state to state to state to state.
Yeah, I think it's pretty much one function. This is, the stuff comes in, you draw it, and you sit around and wait for the next.
Yeah. So, and I talk about this some in the paper. With GUI Easy, the way to really think about it is we have taken an imperative system, Racket's object-oriented toolkit, and put a functional shell over top of that. But when you're organizing a graphical application, we're still going to use a somewhat imperative shell functional core model. So the core of my 10,000 lines of Frosthaven application is a bunch of data structures, enumerations, algebraic data types, things like that, and transformation functions that map from one to another. The GUI part then wraps that up in graphical state and says, when there's a command, a user input that needs to make a change to the state, I'm going to apply one of those transformation functions to my state and get a new state. And as a consequence, all of the things that are depending on that state for rendering are going to update automatically.
How would you describe that's different from what you'd have done if you programmed with the Racket GUI toolkit directly?
With the Racket GUI toolkit, and Matthew, forgive me if I'm wrong, that state synchronization in particular is fairly manual. So I'll go back to the original code here. Right, here's the synchronization of we've had to make this change in our input, but we're not automatically deriving the fact that our canvas needs to update in addition. So we have to manually keep track of the fact that our canvas depends on that editor input and refresh it ourselves.
So that callback looks like it can be anything. So the notion of updating in response to change.
So the callback looks like it could be anything. So the notion that I depend on this input and need to update when it's changed, that notion's been lost here.
Right. The terminology that we use in the paper is that this is ad hoc state management.
Yeah, I kind of want to follow up on that. So in practice, is it the case that you have like one observable that contains the application state, and then you kind of compose functions on it that extract parts of it?
Yeah. So it might be a large record.
Yeah.
My largest application actually uses a record of small observables, which I'm still trying to decide if that was the right design choice or not. An observable of a record versus a record of observables.
Well, the question is, what you have not shown is that if observables compose, right? And I think they don't.
So they do a little bit. You can combine multiple observables into a single observable.
Okay.
This map function
I've presented it as a sort of a singularity, but there's a variablearity version that says take this function f and apply it to multiple observables to create a new derived observable.
And
it's just not shown here.
Okay. And and can you set that resulting observable?
No, any derived observable is
and so that I would
immutable.
suggest is the crucial aspect here, right? This reminds me a lot of the early sort of closure-based wrappers around React, right? So React started out as having that notion of component state that you would imperatively set. Similarly, I mean, unfortunately, the component state was really tied to the component, so you separated out that notion. I think that's a good idea.
Here we get both. So you can have local component state when you need it, and sometimes that's valuable. But for the most part, you have top.
But what I mean is you've separated out the abstraction for the observable, right?
Yes.
Whereas you always have to provide the component with React, right? React has since moved away from that pretty much. So to the point, I think, where it's an anti-pattern, where they really only have essentially immutable application states sort of flowing down into the component tree. The trick with that, to get back to Norman's idea, I mean, the thing with the difference between Big Bang, where you're doing a video game, and this, is that Big Bang, in a sense, is monolithic, right? It's called Big Bang. So, and the trick with that is to get it to be modular, right? I mean, you can split that up, right? But that is actually pretty. I mean, it's not so easy. So we've worked quite a bit on a web toolkit based on React, which has gone through 3 iterations now. I think the last one is pretty good, but the problem is you have an application, right? You have an observable sitting at the top, and you want composition to extend to that. Right? When you have now 2 applications and you want to compose those, right? You already have your observables in place, which tend to be at the top level, right? And how do you kind of have that percolate down? So it's possible, but it requires more machinery, and that I think this sets a pretty sweet spot in being very easy, especially for smaller applications.
That's definitely our impression as well, and I'll just highlight that a majority of the application state that flows through at the bottom level, you don't know if it's immutable or immutable, so you need to treat it like it's immutable. That's why we have these actions that come back up. And then, as I said earlier, right, this notion of extracting domain-specific functions that represent domain graphics certainly ties into a module system.
Yeah, but that's exactly the issue, is that your actions typically flow up all the way to the top, right? And so somebody has to know about all the actions in your application. And if you have really complex APIs, you really want to build components where every component only knows about it, has its own actions.
Yes.
And you can isolate that from the other ones.
I guess I have also a question. So I've played around with functional directive programming, and this seems to be a bit more imperative than... You're taking it already? Okay, sorry. And I wonder if there are things where you think that, like this idiom, where you can shoot in your foot more easily than you wish like. For example, can you, maybe more concretely, is it the case that you can subscribe to an observable and in the subscription update other observables? And if so, can you accidentally or start things where it just keeps updating itself in circles, and you have to deal with that?
I haven't tried to, but I think the answer is yes. The subscriptions are effectively arbitrary callbacks. So here's the new value, do with it what you want. Yes, I think the answer is there are some foot guns, and in particular, like we were just discussing with mutability, trying to update a derived observable is a runtime error.
Okay, but it's not something you ran into, while you were using it.
In practice, and this is actually a feature that I wanted to talk about if we had time. So in practice, I haven't had to use the subscription API except for one case. So on the left, you're seeing the application for our board game, and on the right, you're seeing a web browser view of that application that is run as a server locally by the GUI and updates in reaction to the GUI updating. And when you interact with the web server, it updates the GUI back and forth. And that's the only time I've had to use the subscription API, because I needed to teach the web server how to react to changes in the GUI. But that one very delimited case is take the new values and send them over to the web server side of things.
Okay. Any other? Yeah.
So I think that's often since the original FRP paper came out, it's often been an intuition that we should structure UI toolkits like that. But the thing is that FRP solves the problem of how to compose over time, but what you really want to compose is the values that change over time, right? And FRP doesn't have a solution to that, and that's the bigger problem, right? And that's also why I think Elm originally started out as sort of FRP based, and they've since given up on that concept because this is not where the important problem is, and it's much easier. I mean, that problem, doing things over time is much easier to solve with just saying, well, here's a state, apply a function, there's a new state. That's it.
All right, any final pressing questions? If not, then let's thank the speaker again.
Thank you.
And we have 3 minutes for the transition to the next talk. The next talk will be remote for health reasons, but the person giving the talk is like nearby. We can almost feel them being here, so it's not quite as remote as the remote talks. Start whenever you'd like.
Okay, let me close the ICFP stream. Okay, hello, can everyone hear me? Yes? We're good? Are we live?
I guess we can, I don't know, wait for 2 more minutes or so in case somebody...
Okay.
But we're probably the only workshop that has the 45-minute schedule, do we? So there's not...
Yeah, I believe so. This is also a very generous schedule. This is more time than I had to defend a PhD thesis.
Yeah, okay. Yes, I wouldn't want to start earlier. The question is we have to wait, but I've seen people come in that went for this particular talk, so looks like it was possible. So far, yes. Well, I guess I can start. The intro, welcome to the second half of the second session. Sounds like a geometric progression. Our next speaker is Jeffrey Young. He is in Seattle, but unfortunately, health-wise, decided to stay away from us. But he still wants to spread the knowledge, even not the germs that he may have or may not have. And good to see that you're up and about and not you don't look too. I hope you're doing fine. Thanks for still giving the talk. And yeah, with that, I think you can take it away.
Okay, let me start my timer. There we go. Hello, everyone. So my name is Jeffrey Young. Yeah, I'm here on behalf of my co-authors and IOG, a company I work for, to present our paper, Stretching the Classical-Haskell Compiler, Nourishing GC Domain-Driven Design. So I have the plague, which is I went to 1 day of HIW, and then I got COVID, and so that's why I'm not in person, sadly. So you'll probably hear me cough. I'm sorry if my voice is a little deep sometimes, but we'll just have to make do. If you have any questions, I have my email at the last slide. You can reach out to me or read our paper. I'd appreciate it. Okay. I want to begin the talk with the takeaway message. And I have 2 points. So if these are the only 2 things you remember, I'd like you to walk away with these 2 points. That is, architecture is a choice. So I really think this is a cultural value. And what I mean by this is that Haskell will not save us, but Haskell allows us to save us ourselves. And so what I'm interested in is I'm interested in understanding how we can have the properties of functional languages that we enjoy at a system scale. And more importantly, how do we lose these properties at the system scale level? And then my second takeaway point is that which is difficult to change is difficult to learn from. So if you cannot change your system or your code, then how will you experiment? And if you cannot experiment, then how do you improve, right? How do you iterate? And what I have in mind here is something like a knowledge hazard, but really it's a pedagogical hazard, because if you cannot experiment, then the future systems you were capable of building has now shrunk because you can't learn from your current position. So I'll have more on this later. Okay, so moving into our project, what we want to do is we want to contribute to what I learned earlier this morning from Michael's talk, is the burgeoning functional architecture discourse. And we want to use the classical Haskell compiler as an example. So we want to describe patterns in GHC where, from our experience, we've lost functional properties, and describe how we've lost those properties. Then I want to abstract these patterns from in our experience refactoring GHC with domain-driven design in response to these patterns. So I'm going to begin with a list of caveats because this is a workshop and this is an experience report. First, I do not mean to criticize. It's as old as I am. It is a venerable code base, and it has survived some truly harrowing refactoring, which I think is a testament to Haskell as a from GHC. So I want to treat it as a data point in a continuum of possible systems. I want to think of it as a finch on Simon Peyton Jones' Galapagos Island, and I want to understand how this finch is evolved into its particular niche, something like that.
Jeffrey, short interruption.
Can
you hear me? We occasionally get short drops. They're not horrible, but might be better without. Maybe turn off your video so that your upstream is less, maybe a little bit saved. And I mean, we'd like to see
is
you,
this
but
better?
Let's try this for a while. Yeah, thanks.
Okay, interrupt me again if it happens. Yep. Okay, caveats. My second caveat is that our contributions are not really technical. What I really think they are is they sit at the interface between technology and psychology. And what I mean by that is they're more about how a human interacts with the code base and how the code base guides their hand to propagate, I guess, anti-patterns. So to sum this up, I want to say bugs are written by people. They don't just occur. And then my next caveat is our recommendations are really simple, but that doesn't mean that the problems aren't real. So I think they exist. I hope if you're in this room, you think these problems exist. If you don't think that, I hope to convince you. And then lastly, please interrupt me. This is going to be harder over the internet, but I guess we'll make do. But I prefer interaction over just a lecture or exegesis. Okay, I'm going to get into definitions, and then I'll pause to make sure my audio is good. So when I system, I mean the entirety of a piece of software. For example, for GHC, the system would be its entire implementation, its API, all of its documentation and dependencies. When I say a subsystem, and I'll use subsystem and component interchangeably, I mean a particular piece of the system that is critical for operation. So for example, the core to STG pass in GHC or the parser is a component of GHC, the system. When I say domain, I want you to put on a hat like Connell Elliott, and I want you to think of denotational semantics. So what I mean by domain is I mean the abstract representation that the system realizes. For example, the domain of data.map is information. It's an abstract mathematical specification that our implementation is seeking to realize, which leads me to implementation. This is the thing I work on day in, day out. This is the thing I commit code on the thing that CI runs. This is your concrete project that realizes the system and the domain. Was that okay? Audio-wise, still good? I'll assume yes.
Sorry,
okay.
yes, that is yes.
Okay, great. Okay, now on to the anti-modular anti-patterns. Our first anti-pattern is called shotgun parsing. Here's some code from GHC. It loads interface files, which is how you get cross-module inlining and ad hoc polymorphism and specialization, a bunch of nice features. What shotgun parsing is it's a mixing of processing code with input validation code. Here, the processing code is everything in the special handling do block that it's pointing to at the orange arrow. And the input validation code is this predicate is whole module that checks that the input module is actually either hold and has to get special treatment or not hold and gets default treatment. This term is defined in Alexis King's parse don't validate post. If you Google for it, there's not much that comes up. So I just wanted to show where the genesis of the term came from. Shout out to Alexis if she's in the audience. Okay, so I want to reinforce before talking about why this is an anti-pattern that this was a purposeful design. So it comes from Backpack where with the advent of Backpack, the domain of modules changed. So you had modules as they always were in Haskell 2010 and Haskell 98. And then you also had modules that were parameterized by holes, which could be filled by other modules. And so this note, which is still present in GHC, claims that if we change the data type, which represents a module, then that would make the existing module name and module unit partial. And it would be too hard and require lots of modification. So it was deemed too difficult, and that's why we have a special whole unit value, which this whole module predicate checks, which leads us to the special treatment. Now, I don't think this note is up to date because module name is just text and module unit already has a constructor for whole module. So perhaps it's time to change, but I'll get more on documentation in a bit. Okay, so back to shotgun parsing. Why is this a problem? Well, the first problem with shotgun parsing that's dear to me is it's a performance problem. Shotgun parsing relies on runtime checks, and each of these checks are branches and they can be redundant. What I mean by redundancy is here's some pseudocode, but load interface is called on mod. Interface will check if mod is whole module, right? But it'll complete it. Because that information is never propagated to foo. My internet connection is unstable. And there we go, I'm back. Okay, because that information is never propagated to foo, that means foo has to check if it's a whole module. Okay, so coupling. This is the second problem with shotgun parsing. Subsystems that handle module must always check for is whole module. And that's why this predicate proliferates, and that's how we end up coupling. So here's an instance of is whole module in haddock. I'm not familiar enough with haddock to know why this has to be called. And here's other subsystems will also build on top of this design. So here's the similar predicate in the name module for ghc.types called is whole name, and then is whole name is used in the core component in type constructor Scolum. And if you're curious as to how many instances of these predicates there are, I counted around 56 between just is whole module and is whole name. I didn't check Tycom Scolum or anything that built on Tycom Scolum. So I think that's a rather high number. Okay, so why is this a problem? Continued. Well, I conjecture that shotgun parsing is a major source of bugs. So if we remove all of our special handling code, what happens? The answer is absolutely nothing. Our type check we don't get no type checking error. The type signature doesn't even change. All that happens is a bug is silently introduced. This might not be a problem if your system is small or relatively young, but if your system is 30 years old, trying to get to 40 years old, And if you have a rotating crew of developers that are constantly onboarding and leaving for other projects, then I would say code changes like this are more within the realm of possibility. And so making so that a change like this forces a type change or a type check error, I think is good. Okay, so why is this a problem? Continued. We hypothesized that shotgun parsing leads to bug-driven development. Here's a function in stg to cmm.heap that has lots of type checking code where it's
You just dropped out after where is.
with this module. I just grabbed it because it had 7 guards and looked like it was doing manual. More, we continue to avoid the type system because the status quo in the software system is not to use the type system, it's to add guards with is predicates, right? So this is the kind of, the code is nudging developers into certain implementations, which in this case, I think is bad. It's not avoiding the type system. So the lesson, shotgun parsing results from avoiding typing the domain. We should use types to create a robust implementation. I think that shotgun parsing is performing a manual kind of type checking, like JavaScript's type of. We already have a system in GHC and Haskell that tells us if the inputs are of the right type as defined by the type signature. That's called the type system. And using the type system is declarative. We should use the type system. The domain always has types. So those types are either going to aid you in the implementation or they will manifest as ad hoc runtime checks for special cases. And the reason your domain always has types is because you will always have to differentiate between one thing in the domain and another thing that has a different behavior in that domain. So don't run away from the types, let them guide you. And to tie this up, I think this is a way we lose modularity at the system level because of the coupling with these is predicates that have to proliferate throughout the system. Okay, so my second anti-pattern is layering violations. Consider this code. This code makes a literal integer. This code does not exist in GHC anymore. We've fixed it, but this code is a layering violation. The layering violation is a breach in the abstraction barrier between 2 or more subsystems. Here, the breach is the input dyn flags, and the abstraction barrier is the entire function make literal int. So what's the problem with this? Well, the first problem is that dyn flags is part of the driver. It holds the command line information that GHC is called with.
Jeffrey, you're breaking up again at the end of...
And must, yes.
We heard you until the maclet int is part of the domain. Maybe repeat the last bullet point.
Okay. So the violation is because dyn flags is part of the driver and makelet int is part of the domain. So this might not be clear yet, but I have slides about how this is an exact violation coming up. That was the last point. And then the point I'm on is callers of make literal int must have dyn flags in order to create a literal int, to call makelet int. That means that the caller must import or to import ghc.driver.session. Now the callers component is coupled to ghc.driver.session. And then this means that dyn flag spreads and becomes part of the de facto internal API. So there's a code concept of code gravity that talks about how these massive records end up attracting more and more code, which I have in related works if you're interested. So the problem here is that the layering violation spreads, it's infectious, and it couples components just because in order to make a literal int, I need a dyn flags. Hopefully that was clear. And then to tie this up, this is how we lose modularity and composition at a system level. Dyn flags is essentially like a global mutable variable that's being passed around these components at the system level. So the lesson, One, layering violations have two effects. One is coupling, and the second one is infection. They create paths of least resistance that spread additional layering violations. And I go in more detail in the paper. Okay, now on to JC with domain-driven design. So I won't spend too much time on this slide. Used domain-driven design earlier today, which I thought was very good. But essentially, this is a approach to software development. It comes from OOP. It's 20 years old, and it's about having a domain model that you're programming towards. What we want from domain-driven design is really this philosophy that guides our work called supple design. The idea is to try to make the system as easy to change, easy to experiment on as possible. And we think Haskell's quite good at this. So for example, how much work would it be to swap the parser? How much work is it to add a new backend or target a new platform? I want to reinforce that this is not just an aesthetic judgment. So non-supple designs are hard to change. Because they're hard to change, they're hard to experiment with. Because they're hard to experiment with, they are hard to learn from. This is my second takeaway.
You just dropped out after stating that this is your second
Principle
takeaway.
Here. Still good?
You're back there, but please start again from where you said that this is your second takeaway. I think
Okay, yes. So the second takeaway is because they are hard is the pedagogical hazard. So non-supple designs are hard to change. When they're hard to change, they're hard to learn from because you have a harder time experimenting. This also comes from domain-driven design. I'm going to take a bit of a detour to talk about graphic design. In graphic design, when a graphic designer makes a logo for a brand such as Apple, they construct a document called a brand book. The brand book is the single source of truth for how to use that logo and in what places to use that logo. What does that mean in practice? Well, that means what kind of colors you should place that logo on top of, what kind of colors is that logo capable of displaying. So the Apple logo should either be in black on white or white on black. It should not be in grayscale. So you see here's how to use it, here's how not to use it. It gives you guidance on how to avoid signature mistakes. So do not change the font or alter the spacing, for example. Do not repeat it ad nauseum. If you're going to put the logo on a storefront, how high should it be? How much distance should it be to the edge of the store? And if you're going to put it in a document, how many pixels should it have as a buffer around the logo, right? And these are all described in the brand book. So this is guidance. What I really think this is it's a tool for many individual agents to act consistently. And so I'm asking, why don't we do this for our systems as well? We do this for logos, and I think we should do this for our systems and components as well. And excuse me, this is not a hypothetical problem. So yesterday I was working on some performance regressions in GHC, which is a pastime of mine. And I found this function called find wired in units. In this function is a local function that's described by this this comment right above it. And the comment just says, find which package corresponds to each wired in package, delete any other packages with the same name, and so on and so forth. But package is not represented in the types at all. And indeed, you're right. That comment's from Simon Marlowe. Nope, I lost internet again. Unfortunately,
we heard you until saying that package is not represented in types at all.
Right. Yeah, it's only represented in this local variable name. You might say that this comment is out of date, and you would be correct. It's out of date. The last time it was written,
we heard you until the last time it was written.
It was written in 2006 by Simon Marlowe. So you can blame him. Was that good?
It's good enough. We heard you. Simon isn't here, so we can't blame him directly, but we'll do it later.
Okay, so moving on, I want to say that this is also a current problem. So in the 2023 Zurhack, Duncan Coutts had a language of packages. And so that's the language before Backpack. And so even at the to Cobble or to GHC. And so even in a workshop of experts, we had this problem of not having a ubiquitous language. Hopefully that was clear. So just to be clear, Cobble packages are made up of components. GHC is only interested in library components. These are called units once compiled, and a package is a set of units. And so this is described in a note in GHC called about units, which should really be in the user's guide.
We heard you until in the user's guide.
Of truth. And I'm going to skip the rest of this slide just because I will need the time because of internet problems. So our recommendation is do this, write the guidance, make the brand book, make your naming precise, meaningful to the domain, consistent, documented, and checked by the type system. And I also want to point out that this is happening in other areas of computer science. So Tim Gibru has an initiative, Data Sheets for Data Sets, which is providing guidance on what kind of data sets are useful for particular kinds of large language models, just as you would get a data sheet for like a resistor or a capacitor. And in fact, we've had performance regressions in GH where someone has used the fast string component incorrectly, or I guess not incorrectly, because the module of fast strings did not give guidance to that person on how to use it. So they used it inefficiently, and then we had a performance regression. Okay, my second design principle is layering. So how shall we structure large-scale systems in a functional language? We argue that for GHC at least, we should do this in 4 layers. So this is a layer design. The 4 layers are presentation, application, domain, and infrastructure. And I'll end user, it's any consumer of GHC lib. These are things like GHCI, HLS, event log, program coverage tool, HPC. Application defines the jobs that the system performs and coordinates lower layers to realize these jobs. This is GHC's driver, its build plan, or how the driver makes the build plan, doing recompilation avoidance, that sort of thing. And then domain is everything that the stuff papers are written about. So you might have seen this rather dated compilation pipeline now. In my notation, that looks like this. So it's the parser, renamer, type checker, all this stuff, core, all the backends. And then infrastructure, the idea behind the infrastructure layer is that the upper layers all need these generic capabilities. They need these services. And this layer is the bottom. It provides these services. So that's logging, file system errors, loading it.
We heard you until file system errors.
Oh, that's okay. Yeah. That was the end of my slide. So this is a layer cake. Oh, there's my internet goes unstable. My apologies to the audience. Am I back?
Yes, we can hear you right now.
Great. Okay, so within a layer, components can depend on each.
And no, we don't hear anymore.
Application can depend on domain, which can depend on infrastructure, and so on and so forth. Okay. And then communication should arise through the hierarchy indirectly. to the driver. The driver will say, I need to parse the module, and then I need to take that result and turn it into core, and then take that result and turn it into SCG. In order to do those things, it'll call functions from domain and so on and so forth. That's what I mean by indirectly. And then the module structure should explicitly follow the architecture. And I have an example of this in the next slide. I want to point out the lack of a module called
You broke up after
time reasons.
saying, notice the lack of.
Okay. Yeah. I'm going to skip that point just so I have more time to get to other things. Does this layering realize a supple design? It enables componentization and component-wise configuration. It provides more opportunities to parse, don't validate, because it gives us better abstraction barriers. And it represents the domain in the implementation more succinctly. What I want there is I want to also use the module hierarchy as a way to think about my domain, right? I want it to be a tool of thought. So if I have a dependency that I can't disentangle, I might think, oh, that's very interesting. I've learned something about my domain. And then I want to argue that layering violations become obvious. Here's what I mean by layering violations become obvious. So this is real code in GHC as of 2 days ago. This is the CMM to LLVM module or component. Can you spot the layering violation? I will give you a few moments.
Somebody audience said session.
Someone in the audience knows. If it was Josh or Leita, it doesn't count. They've already seen the talk. So if I explicitly show the layering in my module hierarchy, is it more clear to the people who didn't know? It should be, because you have ghc.present driver session being imported in ghc.domain.cmm to LLVM. And this is what I mean when I say layering violations become obvious, right? Because just from the imports, you can tell. So good to whoever figured it out. So our recommendation is to use a layered architecture and explicitly represent the layers in the module hierarchy. It would be interesting to see what this would look like with a hexagonal architecture. I have not thought about this, but I would love to talk to someone who's more familiar with hexagonal architectures. Although I think the layered architecture makes a lot of sense for a compiler. Okay,
Michael
so
is
my next
nodding
design.
vehemently. Yeah, sorry, carry on.
My next design principle is componentization. So here's some code that performs linking in GHC. It inputs DINE flags. And just from the type signature, you cannot tell what link uses from dynamic flags, right? Componentization is unbundling these components from massive records like DINE flags. So now you can tell exactly what link uses, and its API is I can update or add things to DINE flags in the previous version without changing every call site, right? With this version, now I have to change every call site. And I would say, but that's exactly the point, that you have to change every call site because that would be a type error. And that's good. That's the type system telling you, hey, this has changed, right? And drawing your attention. And then secondly, I would argue with these large records, like 191 fields as in DINE flags, the effort to reach an exotic operating condition is exceedingly small. You only have to change a few before you're suddenly running a GHC that no one has ever run before and that we cannot cover in our test suite. You're way outside of operating conditions. So consider the case where link requires a different kind of component, say special logger. With the new API, this is checked in the type system, and we can provide the special logger without changing tempfs or unit environment at all, which is good. That means our change is more local. Instead, if we supply the DINE flags that is silently changed, we have no idea that it is silently changed in the type system. And if link propagates that dyn flags forward, then it also, whatever receiver of that dyn flags is checking it, won't know that it will have like a special logger in it, for example. So I'm arguing that this sort of behavior, just having these large records, is a way we lose purity at the system level, because it's essentially a global mutable variable that's being changed by each component as it's being propagated through the system. So our recommendation is avoid passing records of functions. Instead, componentize and explicitly pass each component, even if that's painful, which in general, I don't think it is. And we've had a lot of success with this in GHC. All right, my last design principle is component-wise configuration. This is the idea that each component in your system
We heard you until saying the ideal, so maybe repeat the idea.
at extreme. Oh, yeah, I lost you again.
Can you start again from the idea is?
The idea is to treat components as they have their own bounded context, and they should be viewed as if they are external systems in and of themselves. So I'd like to talk to a DDD, domain-driven design expert too, because this might be a bit. Consider the CMM component. The CMM component requires information that dyn flags holds, but it cannot use it because that would be a layering violation. So instead, we do two things in GHC now. First, we define a configuration record that holds all of the information the CMM subsystem needs, right? And this is defined in the CMM subsystem. And then secondly, we define a handshake function okay, maybe not.
We heard you until define a handshake function.
Okay, that's pretty good though. So you define a handshake function in an upper layer and pass it down to the subsystem that requires it, in this case, the CMM subsystem. What this looks like in GHC, this is real code, is here we compute the CMM config using dyn flags. And then we pass that to the CMM pipeline, which is the top level function for the CMM component. And notice that this happens in ghc.driver.main. So this should beg a question if you've been following along. Why not move the init CMM config function into the CMM subsystem? And instead of being dramatic, I'm just going to give you the answer because I'm running out of time. The reason is that this would
You broke up just before saying the reason. We're all excited to hear the reason.
Yeah. The reason is that init CMM config requires dyn. Can you hear me?
Now again.
Okay. The reason was init CMM config needs dyn flags. That's a hint that that function has to be in the application layer. So our recommendation is aggressively isolate components, treat them like separate systems, and isolate by defining system-specific configurations and handshake functions. And in practice, this has allowed us to write tests which were previously impossible, because now we just have to supply CMM config, which only has 9 fields of Booleans instead of 191 fields of dyn flags, where we're just making up information just to pass the record. Again, we want to test normal operating, a normal operating range, not these exotic ranges, which could happen from. Yeah. Okay, good. You can still hear me. Great. I'm going to conclude. Thank you for bearing with me. I didn't have room. Okay, well, I will just list my references. So the Co-Recursive podcast has an interview with Debashish Ghosh on domain-driven design means functional programming. This is in Scala. Alexander Granin has a Manning book on functional design and architecture that explicitly applies domain-driven design to Haskell. Carlo Pesio is a series in code. Am I back? I think so.
Yes,
Okay.
yeah.
Yeah, where the idea of mass and gravity in code, this explains things of how dyne flags, its genesis. I think it's a quite useful concept. I didn't have time to go over it because of our connection issues. And then the Tech Lead Journal podcast has also got an interview with Scott W. I don't know how to pronounce his last name, on domain modeling made functional, which was a book. No? Okay,
No.
there I am. All right, now I'm back. Oh no, it's very bad. Okay.
Shall we move to
the last ref?
Shall we just move to the question section? Or yeah, your final.
Sure.
I mean, of course, the final slide.
This is the final slide. Sure. Yes. Here, I will put everything down. Okay. So please. Okay, we'll call that done. Unfortunately, we had significant connection issues. So if you're interested in this stuff, the paper is Stretching the Glasgow Haskell Compiler. This work was funded by IOG. You can reach me at Dioganu on IRC or at my email, jeffrey.young@iohk.io. And thank you for your time. I apologize for the connection problems.
Yeah, thanks a lot. I think this was a very interesting presentation style because it required the audience to be alert to fill in the blanks when you were like dropping out for half a sentence or so, and it was actually, yeah, it kept people on their toes. I still think we got most of the things you wanted to say, and I hope there are already questions, so let's start ahead with it. We have like 6 more minutes for questions, so some time.
All right. Hi, Will Creighton from Brown. Can you hear me?
Yes, I can.
Great. So one thing I was wondering is how you feel about how this proposed kind of design for a compiler relates to cross-cutting concerns. I don't know about GHC, but one issue in, for instance, the Rust compiler is spans, source spans. These things are pervasive. They exist everywhere. They have to be interned in order to be efficient. And so there's some global context that maintains span interning. And one way in which that's really annoying is every single time you want to test any component of the compiler, you have to make sure to call these context functions that are like, oh, initialize the span session, globals, whatever, or else you get panics of saying I can't instantiate this object. Even if you don't care about spans, you still have to care about this aspect. And so I'm curious if there are those kinds of cross-cutting concerns appear in the in GHC and how that relates to the architecture you're proposing.
Okay. So I didn't get everything, especially the definition of spans. As for cross-cutting concerns, I think that cross-cutting concerns are an extremely hard problem, but they're also ideally exceptions. And so I think that they should be treated as exceptions. They should not be the norm. Whether they exist in GHC or not, I'm actually not too sure, just because I work very deep in the pipeline, and I would argue that most of the cross-cutting concerns are probably in the type checker, but I'm sure someone in the room also can speak to this. I don't think I quite answered your question, but hopefully that was at least a gesture in the direction.
Yeah, that helps. Thanks.
Hello, this is Facundo Dominguez from Twig. So I wanted, so these layers that you have proposed, yeah, these layers that you have proposed make sense. The domain layer in particular is still very large. So would you still would you still hope that it can be organized with the same principles, and or do you anticipate that more considerations will be necessary to make it to break it down into components?
Yes. Hello, Facundo. I recognize your voice. I do think the domain layer is very large, but I also think that treating it as a pipeline makes it very easy to deal with. It also makes it easier for the driver to organize the specific components. Now, whether it should be organized in a further manner or maybe like recursively in another layered type architecture, I am not completely. There we go. I think I'm back. I'm not sure if domain-driven design actually has an answer for this. But I'm also unsure if having large layers is a problem. My actual answer to your question is if we tried to treat the domain layer as another layered architecture, we'd end up I'm sorry for the connection issues. We would end up, I think, with more infrastructure that would be spun out. And then I think we would end up having dependencies that would move to other layers, if that makes sense. So maybe a further decomposition is possible. For GHC, I think the domain layer is pretty well defined and controlled now after the module hierarchy in 9.0. Maybe other GHC developers feel differently. We'll have to ask them. I'm not sure. Hopefully that answered your question.
Hi, Jeff. This is Richard Eisenberg at Jane Street. So you've outlined a couple of sort of ideals in your talk. I really like the different sort of ways to break it down. So there's suppleness, there's performance, which was not a key aspect of the talk, but something that you brought up on the side, and then the I guess sort of I want to call it correctness, in that your first example about shotgun parsing is to sort of have finer grained types. I feel like these are all really in tension with each other, and we can't get all of them. I'm not even sure we can get two of them. And I mean, when you have really fine-grained types, for example, it makes code harder to refactor. I mean, it depends on the nature of the refactor, right? Sometimes it makes it really easy. Sometimes it makes it harder. When you have to break apart dyn flags into all of these components, and then you're copying out aspects of the dyn flags, that takes runtime cost to do that. I'm just sort of curious what your thoughts are on sort of how to balance these different priorities, because or maybe you don't see them in tension. Maybe you sort of disagree with my premise, but I'd be curious to hear about that.
So I accept that there is a bit of tension here, where you have to pattern match on a big record like dyn flags to pull out different fields to make other configuration records, things like that. I think the tension makes more sense if you are trying to hold them as equal goals. And I would argue that I did cite some performance things with shotgun parsing here, but I do not hold performance at the system level as an equal goal. And I think it's fine to recognize where the hot path is and don't be modular there in order to remove certain overheads. So in that sense, I'm willing to bite the bullet that you have provided, Richard. Thank you for your question. I do want to point out, though, that what I'm interested in here is trying to have code that is in a way more self-documenting. And so having a really finer grained types is a way of doing that. And I think that having more type errors is actually a good thing, because I think that leads to more maintainability as long as the type errors are actionable. Whereas with having large dyn flags that are passed around, you won't know that's an error until the test suite tells you, and then it's really going to be some time before you understand it, because now you have to either rebuild the compiler or use some sort of profiling to understand what's happening. And so I would prefer the maintenance, the maintainability of type errors before having this large mutable record be passed around like dime flakes. Now, if performance is more of a, I guess, a goal, there is, and this will be complete heresy to a lot of people in the room, the venerable implicit parameters language extension, which would completely throw maintainability out the window, but then you would avoid pattern matching on large records to pull out fields and you will get more performance. So maybe there's some judicious use of that. I would argue we should not have any use of that in GHC, even if it means our compiler, our compilation time is a few minutes longer. We could just wait a few more years and the M4 Mac will come out and then we'll compile in 11 minutes instead of 14 or something. Yeah, I hope that answered your question.
Okay, we're running close to lunchtime, so one last comment from Michael.
Yeah, so I'll try to make it more a comment than a question. So first of all, I think you're right. It would be interesting to think about hexagonal architecture and moving the lower level in your layer hierarchy down, moving that outside. I think also that domain-driven design has answers for structuring the inside of your domain at GHC, but they're not the right answers because you would think in terms of aggregates and entities and value objects, and I think functional programming has better answers to that. One other way to frame your validation thing was in terms of, I think Ron Minsky coined the phrase, make illegal states unrepresentable, right? This is not necessarily a types thing. This can also be done without types by just having the constructor validate the arguments. Unbelievably, this is something that is completely local to the functional community, even though it doesn't really have anything to do with functional programming. So if you talk to the object-oriented people, what they do is they create all their objects and then they validate with complicated frameworks. And this is like a small thing. So what you said was all spot on. This is a small thing, but this could be a contribution that we make to the larger architecture community, since validation plays an important role in domain-driven design, but they don't know how to do it right. Right? You would think this is completely applicable to object-oriented programming as much as it is about functional programming. So if we were just to communicate better, we would own this, and we're not. Yeah. So
yes.
Thanks. So I agree with everything else you said, obviously, Jeffrey. Thanks.
All right, let's thank Jeffrey again and get well.
Unfortunately, I also wanted to talk to you, but unfortunately that has to happen virtually. One of the ways I view this work is guidelines for negotiating a large code base into a structure that is more easily suitable for parsing and not validating. I believe that was what you had commented on, but it cut out halfway through. So anyway, yes, I'd like to talk more, Michael, and I do think.
So now we can all guess what he thinks. Yeah, I think we should. Let's wrap up here. We start again at 2 with software architecture based on coarse-grained self-adjusting computations by Stefan. And until then, have a good lunch.
Thank you.
Yeah, get better soon.
Yeah, I'll try.
guess we'll get started. So I'm pleased to introduce Stefan Wehr, who's, don't be fooled by his professor title, because he actually has a long career and history in industrial software development. He's going to tell us a little bit about that.
Yeah, thank you, Mike, for introducing. Welcome to my talk, a software architecture based on coarse-grained self-adjusting computations. And this thing is not working. So as Mike already said, I've worked quite a bit in industry, and that's where the motivation for this talk is coming from. Back in 2010, right after my PhD, I joined a company, and we were set out to solve the problem where you have lots of data being produced in hospitals, and doctors and nurses, what they want is a kind of condensed view of the relevant data on mobile devices. And because wireless coverage in hospitals, at least in Germany, was back then very problematic and still is problematic, these mobile devices should work offline. And clearly, if some input data changes, there comes a new radiology image, whatever, then these changes should be propagated rather quickly to mobile devices. And that's what the company was started for, develop a commercial software product for bringing these data not only to the doctors and nurses, but also bringing them in a nice, condensed, sensible view. And before I tell you something about the architecture of the system and give you a demo, I will briefly recap two possible options how to design such a system. The first option is pull. That's quite simple. Mobile devices would then periodically check for new documents, and then the server would compute these documents and send it back to the client. This could cause a lot of redundant work if inputs remain unchanged. There is latency introduced by the poll interval, and also offline is quite hard to support efficiently with this pull approach. And the other obvious candidate is push. So if there arrives new input data, then this triggers a recomputation and some sort of synchronization, send the aggregated documents to the clients. Well, with this approach, offline mode, you can implement offline mode quite efficiently. There is no significant latency except for the time it takes to process the changes and to compute the new documents. There is no redundant work when some input changes. On the downside, well, you waste work if input changes rather quickly and nobody observes these changes, then you do just wasted work. And you need some sort of framework if you want to use such an approach. Yeah, you won't do dependency tracking and all this stuff by hand. And basically the talk is about the framework we developed for this purpose. So I will report on this framework written in Haskell. I will give you some insights into the architecture of the framework. It's on the slide, but it's more on the system where the framework was put to use. And I will also report on about 10 years of experience using this framework and using this software system in a commercial software product that has been used and is still being used in several of the largest hospitals in Germany. The whole framework and also the demo I will show you is open source. You can find it online on GitHub. So basically there are kind of three parts of the talk. First I will show you the API and the demo of the framework, and then we'll come to the commercial application that's using this framework, and then there is a discussion at the end. Maybe some background information, because the title of the article contains the term self-adjusting computations. Maybe not everyone knows what this means. It's pretty simple. The change of inputs should update the results automatically. Then needs to be some kind of dependency tracking in place, and you must cache intermediate results. in the research literature you find about self-adjusting computations, the updates are rather fine-grained, so individual list elements. For our approach, you will see that data updates are much more coarse-grained. So here's a quick example. If you have these 3 inputs, then you could somehow accumulate them, produce some intermediate results, and from an output. And if one of the inputs changes, then you only recompute the relevant parts. Well, I think that's pretty much it. So before we come to the real application, I have, well, basically what I did, I wrote a kind of stripped down version of the application, and that's what you find in the GitHub repository. So that's the architecture, but maybe I will show you first the demo before we discuss this thing here. Where is it? Here. So that's the browser showing the demo. You see it's not very beautiful, and it's also very simple. So what you have here, you have basically 2 views. You have a list of patients down on the left, all patients, where you can find all patients in the hospital, and the recent patients are those patients which have been admitted recently to the hospital. And if you click on one of these patients, then it's self-loading because I didn't start the pipeline, then it will show details. So let me start the pipeline. What do we have here? Let's start. No, what's this? Oh, that's the web server. And what do we have here? There's some kind of simulation which basically simulates the data being produced by the hospital, and then there's finally the processing pipeline which reads data from the hospital and produces the output that then becomes apparent in the browser. So I think so. Okay. There are no recent patients at the moment. Maybe this is a configuration issue because. Sorry. Okay. Okay, then it was just still starting up, or maybe the simulation didn't produce a recent patient at the moment. What I want to show you before you go back to the slides, there is some configuration going on because in the real system there are also lots of parts that are configurable. And you see here, maybe I make it a bit larger. There's one option, recent time, and that's the time after admission to the hospital where a patient stays in this list. So for example, if we now change this to 0, then the list of recent patients should become empty, and you see it changes rather immediately, because the change of the configuration is propagated to the system, and then the list here of recent patients becomes empty. Okay, so far so good. So if there's anything unclear, just ask directly. I mean, you don't have to wait until the end. Where do I need to go back here? Yeah, sure. I'm thinking whether we will see this in a minute in the code. Basically, it works by caching some things, and then the data is in memory. And yeah, you have to, in this case, we filtered a list of all patients to produce the list of recent patients based on the time.
And so when you change the time, you just do a full scan.
Yeah, you rechange the list of, I mean, not the list of all patients with respect to the total history, but with respect to all patients that are currently admitted to the hospital. Yeah, we have to rechange it. Yeah, that's what I mean with coarse-grained. If you look in the literature of self-adjusting computations, then you can really do updates on the granularity of individual list elements, and that's not what we are doing here. Okay, so that's the architecture of the demo, and I will show you on the next couple of slides how the demo has been realized in Haskell. So you see here basically three sources of data. There's here something called import store. That's an event store for data coming from the hospital. So this import store contains data about patients, data about medical reports. I think for the demo I didn't model medical reports, so it's basically only patient data. Then there's here something called workflow store. That's where interactive data produced by nurses and doctors goes into. So if a nurse puts down some note for a patient, then this data enters this workflow store. And there is the configuration. You can configure various aspects as we've just seen before. And these three sources of data, they flow into this pipeline of self-adjusting computations to produce here for the demo, they produce directly a model for the UI. This component is called a file store. That's also some kind of event store. And then the HTTP server sends the data to the web browser. Okay. So and I will now show you, there's a screenshot where you can see the three parts of the GUI, but we've already seen that. I will now show you how the main things are realized in Haskell using this framework. Because I mean it's using a framework, so there are some things which you need to know from the API of the framework. So that's the computation here on the top for reading the configuration. So before you can use a computation, you have to define it. Define comp defines a computation. You give it a name, and then there's a caching strategy. I will explain two different caching strategies later on. And basically, this part here is then the body, the logic of the computation. And from the type of define comp, you see here, that's the type of the body. P is the parameter of the computation. R is the result, and everything is running in this comp M monad. And you get back a compdef value from define comp. And what you also see in the body here is comp source rec. That stands for computation source requests. This comp source request issues a request to a computation source because the framework abstracts over different kinds of data sources where input data comes from. And in this case, file source is some source accessing files on disk, and read file is a request to read a specific file. Okay, so that's quite simple, getting the configuration. Then the next part is how to generate a list of all patients. We do this in two steps. In the first part, we do an over approximation. It's basically a fold over this import store, over the event store. And we visit each event only once. And we do it in two steps because in the first step, we don't want to depend on a configuration, because depending on a configuration might mean we have to visit an event a second time, and that's something we want to avoid. So, and folding over something, there is a second kind of function for defining a computation. Define incomp defines an incremental computation. That is a computation that is feed again and again with data keeping some intermediate state. Basically that's the initial state, and then the F does the fold, consuming new events from the import store and updating the state of the fold, producing a new state. Okay, and then in the second step, we compute or we generate the real list of all patients by taking the configuration into account, because it's configurable how long before admission and how long after discharge a patient should be visible. And with this, you see that such a computation definition here can refer to other computations. So this computation definition is parameterized over the computation for accessing the configuration, and that's the computation defined on the previous slide for generating the complete list of patients. And then what we do in the body here, we call these computations. This is eval, comp, or fail stuff here and here. we can access the time at a certain granularity, and then we filter the complete lists of patients with respect to the configuration and the current time. So that's basically the filtering here, and yeah, and that's the complete list of patients that are currently in the hospital. Okay, good. So far so good? Okay. So then there has to be some wiring to bring all these computations together, because we have seen on the previous slide, certain computations can accept other computations as arguments. In our framework, you have to wire them explicitly. There is a monad comp wire M for this, and that's how it looks like. I mean, you take the computation definition, or maybe we look at here, wire comp takes the computation definition and gives you back the runtime representation of a computation. And this thing you can then pass here to other computation definitions to drive the wiring. Okay, so that's basically how the framework in general works. For the demo, there are also some computation for generating the outputs. I've omitted these because it would be too long and probably also too boring. And there is also a type class called compsync, which is abstracting over the outputs. So we have abstraction facility over different input sources, and there is an abstraction over different kinds of outputs. And the output of this demo, at least, is the UI model of the application. And basically, it's a simple markup, kind of markup language, which for the purpose of the demo, I just modeled with Haskell data type. So we have a document here which has a title. SL is a strict list of sections, and a section has also a title and a list of content, and so on and so on. One thing I want to talk about briefly is caching. The framework caches intermediate results, and there are two main modes. The first is full caching. Then this means the full result of a computation is cached, so that the result can be reused if the same computation is called again with the same arguments. Clearly, there's always, if you choose full caching, then you have to do some sort of trade-off between how large is the result and how much time takes it to recompute. So that's up to the user of the framework whether he or she uses full caching, or the alternative is hash caching. There we do a large hash, or we compute a large hash value from the result of the computation and only cache this hash. Clearly, then you need to re-execute computation calls when they are called again, because we don't have the result in the cache, we only have the hash. But it's useful as a kind of dependency blocker that's very used at some places. So if computation C1 calls C2 and C2 calls C3, and here C3 changes, but this change does not cause C2 to change, then you don't have to re-evaluate C1. That's what I mean with a dependency blocker. Okay. So basically that's what I want to tell about the API and the demo of the framework. And now I will report a bit on the experience I made using the commercial, or using the framework in a commercial application. Maybe first some background on the application. It's as you've seen, a health information system. It's used in several larger hospitals in Germany. It has been developed and is still developed by a small company in Germany. Users are doctors, nurses, and there are also patients using the app. There are two front ends, web and mobile. There is an offline mode, as I said at the beginning. And the application has, I would say, 4 main features. So you can access the electronic health record, the EHR of a patient, in a read-only fashion. You can write some fields of the EHR. These are 2 features, and the other 2 are it allows collaboration between doctors and nurses, so they can exchange messages and so on. And it also allows patients to communicate with the hospital. So how does the system gets the data from the hospitals. Hospitals, at least in Germany, I don't know about other countries, but I could imagine that it's similar elsewhere. So hospitals in Germany, they store patient data and other data really scattered over different sources. So this piece of information you find in this system and some other piece of information in some other system. And that was really the initial motivation for providing a system which somehow aggregates information from different sources. And two main sources are HL7. That's the standard encoding patient data, patient reports. It's an event-based system. That's the main point here. Another thing is HL7 is meant to be the standard, but every hospital I know uses its own, let's say, dialect of the standard. And then another important standard is DICOM for accessing medical images. This is a query-based data source. And there can also be various hospital-specific systems for accessing whatever kind of information. Here are some numbers. I asked my former colleagues to look at a large system to give me some numbers of the current state of affairs. And this is what they sent me. So 140,000 HL7 messages per day with 1.6 terabyte of disk space, 10,000 patients, 230,000 reports, 6.5 million DICOM images, and only 500 users. That's because not all doctors and nurses in the hospital are using the installation where my colleagues looked at. Probably also interesting is the implementation uses several languages. Clearly Haskell is mainly, the backend is mainly used in Haskell, but we are also using quite a lot of TypeScript code for doing client-side scripting. Then there's Objective-C code for the deprecated iOS client, and we have Dart code for the new mobile client.
75,000 lines of Haskell.
Yes.
That's probably the biggest Haskell program in the world.
I don't know.
A lot bigger than GHC.
That could be.
That's a lot.
I counted the lines by myself. It includes comments, but there aren't too many comments, so that should be. Okay. So that's the architecture of the whole system. It's a bit more complicated than for the demo. So, and there are basically 4 steps, and I will now explain them individually, reusing parts of this graphic here. So I won't explain everything on this slide, but go part by part. So the first part is the import. How does data comes into the system? I've already said there are various data sources in the hospital, and that's why also the framework provides an abstraction for data sources. For example, there's a communication server which in a hospital, that's part of the hospital IT infrastructure, and that's here our system. And this communication server, it sends out HL7 messages on various occasions. A new patient is admitted, patient is discharged, and so on. And then we have here an import component. For DICOM, we have another component. And you see here, HL7 is somehow event-based, so the communication server sends a message to our system, whereas DICOM is query-based, so our system queries here the DICOM server in the hospital. The next step is then interpretation. The purpose of the interpretation is to bring hospital-specific data formats into our domain model. You could now say, why does every hospital has its specific data format? Well, I don't know, but that's the case. Essentially, all data formats contain the same kind of data, but it's different. And that's why we bring it here into our domain model. So for example, that's part of a HL7 message. CRP, it's some inflammatory value, and it then gets transformed by the interpretation, here driven by self-adjusting computations into our domain model. Now you see here the domain model is then persisted. So this blue thing is it's a persistence layer. It's persisted in a component called file store. The file store is essentially a multi-version document store. It works similar to an event store, or it has certain functionality of an event store, but it deletes unreachable data after a certain amount of time, because otherwise we would simply run out of disk space. Okay, so far so good. The next step is then take the data from the domain model and map it to the UI model, which then can be synchronized to the users. And that's here. And I mean, that's now pretty similar to what we've seen before. There's also this workflow store where user input is stored. And from the workflow store, the file store with the domain model, and from various configuration files, a pipeline of self-adjusting computations compute the UI model. And here, the CRP example in the UI model would look like this. You see here, there is no meaning whatsoever of a laboratory value called CRP. It's only a key value cell, and the rendering could then look like this. There's also an export manager which brings back certain data into back to the hospital. Okay, and finally, well, that's now pretty simple. There is a synchronization component which reads from the file store here. It's an event store, so the synchronization server gets events, and then it has to compute which document needs to be sent to which client, and it does so. Okay. So that was basically the architecture of the whole system, and now I've prepared some slides with hopefully useful insights I gained during the 10 years where I was working with the system. As I said, the development started back in 2010. It's still alive, meaning it's still running in several hospitals. And from my point of view, I can say the framework was flexible enough over the years so that we could add several extensions. So we added these export functionality you've seen on the previous slide, on 2 slides before. We've added at some point later. We implemented something called demand-driven generation of outputs. I'll talk about this in a minute. At some later point, we've added client-side scripting later. So it turned out to be quite flexible. Clearly, when developing such an application, there are other aspects besides computing the correct kind of data. So privacy, security, regulatory affairs, deployment, whatever. But for this talk and for this paper, I ignored these aspects. They're important, but not for this talk here. Okay, so from my point of view, the computation framework has shown several benefits. So first of all, it provides really the foundation for supporting offline mode. So you need to pre-compute the documents if you want to have a true offline mode. I mean, you could always do offline with some sort of caching, but then users could only access those documents that they've accessed at some previous point in time. What we've also seen is it was very good to have no redundant computations if user access the same data multiple times, because that's what's happening in hospitals. The users they are looking at the same data, or various different users are looking at the same data all the time. And if you would recompute it every time someone looks at it, this would be much too expensive. And it also scales well with the number of users. So if you add a new user to the system, there is not much work to be done, because everything is already computed, at least if the new user has the same view configuration as an existing user. So if each user wants to have its own fancy view configuration, then it becomes too expensive, but that's why we try to keep the number of view configurations quite low. Clearly, there are also disadvantages. The biggest disadvantage, at least the way we implemented it, is long startup times. So if the system crashes, which really happens rather rarely, but also if a system needs to be updated, then it takes quite a long time until it's up and running again. Up to 2 hours here, and that's why, because the internal state, or we did not persist the internal state of the computation framework. I mean, you could do it. At some point, we tried it, but then something else became more important, so we suspended the persistency layer. So I think it's not impossible to do, but we just didn't do it. Also because 2 hours sounds really pretty bad, but the system is still kind of working during this time. You can access all data in a read-only way. You can also enter new data, but you won't see any new data coming into the system. So that's not really good, but it's not that the system is completely down and you cannot access anything. Okay, so another disadvantage is what happens when the number of inputs increases. Let's say the number of inputs doubles. Number of patients, you have twice as much as patients as before. Then clearly you need to do at least twice as much as work as before. And this at some point really became a problem. And then we realized, okay, many of these patients, they are not accessed very often. So there are a certain set of patients, they are accessed all the time from our users. And another set of patients, they are really accessed only very rarely if they have night shift, for example, which only happens 2 times in a month or so. And so we said, okay, for these kind of patients, we generate the outputs on demand. So only if the user clicks on one of the patients, then the whole data set for the patient is generated. Clearly, these patients aren't synchronized for the offline mode, but nevertheless, it was a good trade-off. Okay, so there's one slide comparing push versus pull. What you can, or what's the case? Pull does work per client-side request, and with the push approach, you do work for every input change and for every output. And if you want to decide for your application whether you want to have pull or push, then then you have to look how often does input data changes, how many client-side requests do you have, and how many outputs do you have. For our application, it's the case that update rates in hospitals are rather low. So here 5 updates per second, but most of the time much lower. Many outputs are accessed frequently, so that really means the push thing here works out pretty well, especially if you combine it with this on-demand generation of outputs that are only rarely used. So one last slide about Haskell. Is Haskell important, or could you do the system in another language? Well, I think you could do it. Also in another language, there is nothing especially important, or it's nothing that prevents you implementing it in another language. But having control of side effects in Haskell is really nice, because these computation bodies, they are re-executed at some later point in time, so you don't want to perform arbitrary side effects, because those would be just repeated. And we also use the free monads trick to suspend computations. Laziness in Haskell is sometimes in the way. I mean, we all know space leaks triggered by too lazy data is a problem. So at some point in the project, we decided to use the strict data flag. So in the whole project, all data types, all fields of all data types are strict by default. There are some data types which are explicitly marked as lazy, but not very many. And sometimes, or not only sometimes, monitoring the execution of a Haskell program can be really challenging. If you want to know what's going on, then it's not too easy to answer. At least back when I was working with the system, I think such things also improve over time. Okay, so short summary. What I've shown you, software architecture based on self-adjusting computation implemented in Haskell in development and operation since now 13 years. The software runs in production, and you can access the framework. And I mean, it's not the original framework. I simplified it slightly, but it's taken from the production code. You can access this in the GitHub repository, where you also find the demo code. Thanks for listening, and feel free to ask any questions.
Thanks. Every time I hear somebody talk about incremental computation, I think this looks like a build system, and every time I see somebody talk about build system, I think like this looks like incremental computation. Is there a fundamental difference between these two, or why could you have used Shake, the library, inside the thing and would do the same thing, or?
Yeah. So in the paper there is a discussion about the similarity between Shake and our system. Actually, I'm not totally up to date whether Shake now supports a continuous mode. But back when I was working on the system, Shake was simply execute it, run it, and then it's done, and that's it. And our system is running continuously, watching on changes of inputs, producing new outputs. I mean, there are also build systems which do exactly this task, running continuously. So there's definitely a large similarity. True.
Hi, Stefan, thanks. You started off telling us about pushing notifications from the data store to the clients, and then on the diagram sometimes there's updates sometimes of some fields somehow go back to the data source again. There was this kind of out of band error for sending, I forget what slide it was. You had there we go, 2 slides forwards from that. Oh, well,
so
here, from the export manager back to the hospital.
Yeah.
Yes. So there's no connection between the sort of read view and the write view of this data. The writes just go back somehow. Maybe they're sent by post, and sometimes somebody in the hospital opens the envelope and puts the thing back. I mean, did you? It looks like it wants to be a lensy kind of thing, where you present on the mobile devices and the web browsers not just a view of the data, but allow people to update the data or update some of the fields of the data, and that you could have a more principled connection between the reads and the writes.
Okay. Now that's a good question. I think the answer is the life is quite simple, because the data we send back here, it's sent back as a PDF or as PDF that's archived somewhere, and that's it basically. Right. So yeah. It would be cool to have some kind of interactivity where a user fills out a form here and it gets sent back to the hospital, and other data are integrated into the same document and then sent back to the user. But it's not as complicated as this. Yeah.
Some of the red arrows could be bidirectional things rather than just unidirectional things.
If we would need this kind of extended functionality, yes, but really this arrow here is only
PDF.
Send a PDF to some archive, and that's it.
I wasn't so far off with the envelope.
Yeah.
Any other questions? We got plenty of time.
So one of the interesting things about self-adjusting computations is you have bind, and bind gives you the ability to like dynamically reconstruct parts of the graph in response to changes to configuration or changes to data. I'm curious how that dynamism did or didn't play out in the design. Did you like depend on the ability to kind of dynamically reconfigure the graph?
What do you mean with dynamically reconfigure the graph?
So you can imagine a system just like this, which is just uses like the map-like parts of the monadic interface, so in applicative rather than a full monad. And in a system like that, the structure of the graph is known statically when you construct it, right?
Yeah.
Once you have a monad, not so much. Now the bind can refire at some point in the middle of the computation, and you can construct a different subcomputation.
Yeah.
Right. So you could have something which at startup depends on 5 different inputs, and then like something changes. You're like, no, now I want to depend on the totally different 50 set of inputs. You can reconstruct the graph as you go. And I'm wondering, like, was that dynamism important to this application? Or could you have gotten away with a more static graph?
No, it's important to the application. For example, I mean, you can change in the configuration, you can change all sorts of things, which can, for example, enable a complete new kind of view. And for this new kind of view, you need to fire different computations. Yeah, so you need this dynamism, definitely.
Any other
questions? I'm impressed by the size of the project, and I would like to ask how far did you go with the stronger typing here? Where is the balance? To get too far with it, or there is some balance that is good for the teams to work on such a big project in some simpler way or something like that?
Yeah, very good, good question. It's more Haskell related or type system related. So my point is keep it simple, stupid. So really only use the basic things of Haskell's type system. We have some type classes for serialization, for pretty printing, all the basic stuff. Algebraic data types are used quite heavily, but we don't really use more advanced type system features.
And very few type classes.
There are not too many type classes, right? Yeah. So yeah, basic for pretty printing, serializing, maybe 2 or 3 other purposes, but not too many. Yeah.
Thank you.
All right. Well, let's thank Stefan again.
Thank you.
So, and for timing purposes, we need to take a 90-second break. That might be a good opportunity for people to come in and take a seat. Excellent. So welcome Jeremy Gibbons, who's spent a lot of his life making life easier for programming in the small. So I'm gratified that he's turned his attention to programming in the large. And I expect great things. Go ahead.
Right, thanks, Mike. I hope I live up to your expectations, because indeed this is not what I normally do, perhaps. But so there's this wonderful XKCD cartoon showing the movie character interactions, and there's one for Lord of the Rings that shows all the different parties, the Fellowship of the Ring and so on, and Star Wars and Prime is down here, but Lord of the Rings is the one I want you to focus on. If you've read the book, and I guess also the movies, but if you've read the book, I remember that it was formative years for me, and it follows this group of characters, and they split up and they go off and do different things, and then they re-merge, and this XKCD cartoon shows how they interact with each other, and how the parties, so here's Boromir joining them, and then that's the end of Boromir at that point, so if that was a spoiler. The parties split and go their separate ways. And it can be helpful to see this in order to understand what's going on, but that's absolutely not how the story is told. And the story is told from the perspective of one of these parties following along their path, their destiny, and then cutting to another one of the parties. And so the book is split up, and you spend quite a long time following one set of characters, and then you, meanwhile, back at the ranch, you go and cut to another set of characters. And that phrase, meanwhile back at the ranch, is, I mean, it's a cliched caption from silent movie era westerns, but it's become a slogan for movie making, and Hitchcock used it as, so Hitchcock said this is a good piece of storytelling advice. You want your story to be split up into several parts, and you focus on one part for a while, and maybe when that bit gets boring, or maybe more importantly, when that bit reaches a cliffhanger, you cut and you go and tell another part of the story. And I think it's a metaphor for software architecture as well, because we want to tell the story perhaps out of chronological order. We want to follow one part of it and explain how that goes, and then say, meanwhile, back at the ranch, here on the server, something else is going on. And you don't want to have to keep cutting backwards and forwards to say what all those individual parts are. So I had some work, which is kind of small-scale things, but I saw the call for papers for functional software architecture, and I thought that sounds cool. And I'd like to make the case that this particular gadget that I've been working on has applications here. So let me see if you buy that case. So now another story. Meanwhile, back at a different ranch, 1972 is it? This book. The picture's not very good, but it's the structured programming book by Dahl, Dijkstra, and Hoare. And so Dahl, Dijkstra, and Hoare each have a chapter. A part of this book. And Tony Hoare's chapter, among other things, is the one that incorporates this quotation. There are certain close analogies between the methods used for structuring data and the methods used for structuring a program that processes that data. The shape of our computations follows the data that they process. And that's the motto by which I live. And all this stuff about data type generic programs and functors and categorical structure, algebraic structure in programs, that's all foreseen by Tony 50 years ago. He didn't see it in quite the same way, but it's a message that persists, and I think it's absolutely the right way of thinking about programs and where do they come from. Around about the same time, I think it's 1976, there's this book by Michael Jackson, the other Michael Jackson, called Principles of Program Design, which was about he didn't call it this, of course, but now Jackson Structured Design, this design methodology for structured programming. And he says again, the central theme of this book has been the relationship between data and program structures. The data provides a model, and by basing our program structures on the data structures, we ensure that our programs will be intelligible and easy to maintain. And so you sketch the data, and to some extent, you don't need to explain anything more about the program. It just does the obvious thing with that data structure. And that was there's a quote from Fred Brooks about, show me your code and I will be confused. Show me your tables, your data, and I won't need to see your code. It'll be obvious. So function follows form again, except that it doesn't always work. And also in Michael Jackson's book, a large part of the book is about what he calls boundary clashes, what's also called structure clashes. So these are when your data is inconveniently in different formats. So in particular, when the input data is in one format and the output data is in another format. So input data is arranged one way and output data is arranged another way. So input data is arranged by character following their storylines, and output data is arranged chronologically the timeline of all the movie characters. And what do you do for your program then? Well, you can't follow both of those structures. You have to pick one somehow. You have to reconcile those differences. And so that he has examples. A lot of the examples are sort of regrouping stuff. So where you have a long piece of text split up into punch cards of a certain width, and you want it in punch cards of a different width, then you need to sort of take you can't just follow the punch card structure directly. You need to sort of take it into a sequence and then take it out again to sequence broken up into different sized chunks. So the intermediate structure, the sequence structure, is not the input structure, it's not the output structure, it's something else, because these disagree, and you have to come up with some way of reconciling the two. Or alternatively, you have some stuff that's row-oriented and some stuff that's column-oriented, and one program structure doesn't give you both of those. So you might need to transpose half of the data to get it in the right arrangement, so that then you can do some nice data structure oriented, the data structure determines the program structure, zipping two things together. And I think lots of software is like that. We can't always follow the ideal view of the data structure is all there is, and you just turn the handle, the program structure matches it. Sometimes there are messy, awkward mismatches that we need to reconcile. So that's my story. What do we do when we have these structure clashes? And I argue that you want to separate, in many cases, not always necessarily, in many cases you want to separate the specification of a computation from the execution of it. So I'd like to, well, explain what these set of characters do, and then separately explain what those set of characters do, and then set them on their way, and time evolves, and you get the XKCD timeline chart. So I have one of those gadgets, which I'm trying to sell you, a data type that allows you to separate the specification of a computation from the execution of the computation, which I'll tell you about. It turns out to be an applicative functor, which is kind of like a monad. It's a way of capturing effectful computation in a pure language. I'll try to skim lightly over that because I'm not assuming everybody has seen that and knows what it is, but think of it as a representation of computations. And I'm going to start off by showing you two-phase computations, and then we're going to generalize that to multi-phase computations. And it turns out that the two-phase ones we can make heterogeneous in the class of effects. So the first phase can use one class of effects and the second phase can use a different class of effects. Whereas the multi-phase one is going to have to be homogeneous. They're all going to have to use the same class of effects. So that's rather like pairing and lists. So pairs, the type of pairs, you can have heterogeneous pairs. The left-hand component of the pair can be a different type of the right-hand component of the pair. Lists are just iterated pairing. So cons is pair, and you just recurse in the right-hand component, and you get lists as we're familiar with. But when you do lists that way, you typically make them homogeneous rather than heterogeneous. I'm going to show you some toy examples, which I hope will be motivating and convincing examples for the gadget. And then I'm going to end up with some conjectures about functional software architecture and thinking about multi-tier, three-tier architectures and so on, but particularly thinking about choreography. So I was inspired by the Haskell paper. That's why I'm here, is because of the Haskell paper. So a lovely paper and well-deserved Distinguished Paper Award, and a nice talk again. So I read the paper and I thought, oh, I could do that, and it fits this pattern. I think, I confess, I haven't actually done it. So this is kind of a sales pitch for collaborators, perhaps. So here's some Haskell. There's this class of applicative functors. So again, just think of notion of computation. There are two components to the interface. There's this pure and the asterisk in angle brackets, which is a kind of funny application. So think of F the type f of A being computations that have some class of effects and return a result of type A. So they might be I/O computations or non-deterministic computations or mutable state computations or whatever. So pure is a way of turning a plain ordinary value into a computation that is allowed to do effects but doesn't actually do any effects and just returns that value. And the funny apply is a kind of sequential composition. It's a sequential composition where the left-hand part might have some effects but then yields a function. The right-hand part might have some effects, then yields an argument to that function, and then you apply the function to the argument and you'll get a result, collecting the effects from the left-hand side and the right-hand side as you go. So you might think of the pure as being a kind of skip and the funny apply as being a kind of sequential composition, and these are monoidal. So sequential composition is associative, sequential composition is the epitome of associativity, and skip is the neutral element. So that's a good metaphor to have in your head. And then there's, on top of that, there's a notion of traversable data structures. So traversable data structures are data structures where you can go over all the data structure and visit every element. So they're container data structures, they have elements in. You can visit every element with a function, an effectful function. So the elements are of type A, you can turn them into things of type B, but you might incur some effects when you do so. So maybe you turn A's into B's and using some I/O to do that. And if you can do that for each element, then you just do it for each element in turn on your tree of A's or whatever it is, and you'll get a tree of B's, but incurring a whole bunch of effects as you do. And again, there are some sensible, the laws to make sensible instances of these, but just think, go over a data structure and visit every element precisely once. You can do it in arbitrary order. This doesn't constrain the order, but you have to visit every element and you have to do so precisely once. So for example, here's how to traverse lists. In Haskell, I should have written square brackets for that. That's the list functor. To visit all the elements in the empty list with this body f, well, there are no elements in the empty list. So what you return is the empty list, but you do so, that's just a value. It has to be a computation, so you use pure to inject that. And to visit all the elements in a non-empty list, well, this is going to do it left to right. So it's first going to visit the head, and then it's recursively going to visit every element in the tail. And the interface here for applicatives is Conor McBride and Ross Patterson's interface, and it's very carefully chosen so that it looks like application, and you can write things that are just kind of application written in a different color almost. So you visit the head of the list, you visit every element in the tail of the list, and you put the results together with list comms. So this is almost like writing map over lists, and this is how you would write map over lists, just with some extra bits, and that's scattered across the top, really. Now, here's a different data type, trees. So my trees here are general rows trees, they're sometimes called. It has a root label and a list of children, and each child is a tree. So it consists of an element and a list of subtrees. And so here's a tree with root label 3 and 2 subtrees. And you can traverse that too. So you can traverse it, and I'm not requiring you to do it in a particular order, but here's kind of the natural order. You can traverse this tree depth first. So there's only one kind of tree, nodes, so there's only one case for the traverse function, and you traverse the root, you traverse each of the children in left to right order, and then you put the results back together again with the node constructor. So actually what's going on here is this traverse, what's that? There are trees and there are forests. A tree has a forest of children and a forest is a list of trees. They're mutually recursive data types. And so the functions on them are typically mutually recursive as well. So here this is traverse over trees and there's traverse over forests. And traverse over trees calls traverse over forests, and traverse over forests calls traverse over trees. They're mutually recursive too, following the data structure. So following Tony, following Michael Jackson, this function follows the structure of the tree data type. So this is a recursive call. This visits every tree, every subtree using traverse, does it for every element of the list. So that's list traverse is the outermost one. So for each element of the list in some order, we're going to visit all the elements of that child. Now, which order we're going to get for list traverse, it's the one we specified when we specified list traverse. But perhaps you can see, if you do this, you'll visit the root, and then you'll visit everything in the first child, and then you visit everything in the second child, and so on. So this will be a depth-first traversal over the tree. And this is so straightforward, so determined by the data that you don't have to write it at all. You can get GHC to derive it for you. But that's depth-first traversal. What about breadth-first traversal? That doesn't work nearly so nicely because, so to speak, it cuts across the grain of the tree. And so I've spent some time in my life thinking about breadth-first traversal. My first ICFP paper was about that as well, a long time ago. So that's a cliffhanger. Meanwhile, back at the ranch, I'll have a drink. So here's another problem. This is one due to Richard Bird. And it's called the rep-min problem. And it involves taking a tree, finding the minimum element in the tree, and replacing every element in the tree with that minimum element. So this computes the minimum element of a tree. This does the replacing of a tree, every element of this tree by this value. A minimum, there's something for minimum of trees, a minimum of forests, a minimum of trees calls minimum of forests, a minimum of forests calls minimum of trees. Same pattern again. Replacing on trees, replacing on forests, replacing on trees calls replacing on forests, replacing on forests calls replacing on trees. The same pattern again. Those both exactly follow the structure of the tree data type. So, but the tricky thing is you're supposed to do this in one pass rather than two passes. You're not allowed to go once over the tree to find the minimum element and then a second time over the tree to do the replacing. So Richard used this in a paper in 1984, I think, arguing for lazy valuation and let rec and in your language, because there's a nifty cyclic functional program that does it in one pass. Now, whether it actually does it in one pass, I'm not going to get into that. And you might argue, I think you might reasonably argue about whether it's doing anything any better. And it's true that it's not any faster than doing this. But here's Richard's program. There's an auxiliary function, and again, one for trees and one for forests, and they're mutually recursive. The auxiliary function takes a tree of integers and some replacement thing of some arbitrary type A, and gives you back the minimum in that tree of integers, which is an integer, and then another tree of the same shape that you first thought of, but with this A value instead of the ints that you started off with. And because min t and replace t both follow the shape of the tree, they have the same shape, so these two computations can be fused into one. One is sometimes called the banana split theorem. They're both folds over the tree, they both follow the same structure, and so you can write one fold that generates the pair of results. And that's exactly what's going on with this augs function here. So there's no magic in the augs function. It's just the thing you would easily write that does both the minimum and the replacing in one go. And no cyclic, nothing fancy here. The only clever bit is the first line, because what we want to use the augs function for is the replacement value should be the thing that we could compute as the minimum. So that's done with this let. Augs t produces a pair um, and that m is also the input to the function. So this let is a let rec. It only works because of that. You're allowed to have that cyclic dependency, and it's not actually cyclic. And you can verify that by seeing that, let's see, the int that comes out here is independent of the A that went in. In fact, even from the type of the polymorphic type of args_t, it's apparent that the int can't depend on the A because there's nothing you can do with the A if it's polymorphic. So even if you don't know what the what the M is that goes in here, you will get a sensible M out, and therefore it's productive. So you will get some M to feed in. So that was Richard's paper in 1984. He is a bit before my time, but he must have talked about this at IFIP Working Group 2.1, which is the squiggly program transformation calculation kind of working group. And Alberto Peterossi, who's also in that group, I infer, heard the talks and said, yeah, you don't need to do that. Here's a better way of doing it that doesn't involve laziness. So the difference is rather subtle. Watch this type here for args_t. This one takes a tree of ints and produces the int, the minimum as before, but produces a function as the other thing, which is the dependency between the output tree and the input replacement value. So it's computing a higher order. It's a higher order function. It computes the function as a result, as one of the two components of the pair that it returns. So you call args_t and you get two things, but now m is the min as before, but u is a function, and you apply u to m. And the call of args_t is not circular anymore. And so you don't need a let_rec, you can just do it with a let. And so Alberto said you don't need all this fancy lazy stuff, you can just do it with higher order programming instead. I mean, to my shame, I didn't know this. I know Alberto very well, and I've been a member of 2.1 for donkey's years, and this is not widely known and not widely cited. It doesn't help that it's in published in obscure places, but Richard's example is a kind of a canonical example of lots of program transformation, program calculation papers. So what's going on here? What's the relationship between these two? Well, I'll tell you that story as well. And what these have in common is about traversals. So if I have, so now this is another operator. It's a pairing, a kind of zipping operator on effectful things. If I have a computation that returns A's and a computation that returns B's, I can sense run one after the other and get a computation that returns A-B pairs. So if I have a traversal that produces a tree and a second traversal of the same tree, so the same shape of traversal, combining, so one traversal uses F on every element, the second traversal uses G on every element. Can I do that? Can I fuse those two traversals? Can I do that in one traversal rather than two? So can I do it with a single traversal that does F and then G on every element? And that will give me a tree of pairs, and what I want to end up with is a pair of trees, so I have to do some unzipping afterwards to make the types match up. Can I do that? No, obviously not. If you do the left-hand side, traverse the tree everywhere and do F on every element, and then traverse the tree and do G on every element, you'll get all the F effects before any of the G effects. Whereas the right-hand side interleaves the F and G effects. So obviously, in general, those are going to be different. Now, if the class of effects is a commutative class of effects, so if it's reading from a context or probabilistic choice or something like that, you don't mind the interleaving. You can't observe the interleaving. And so you could say those two things agree. But that's very restrictive. You can't do I/O, you can't do stateful stuff. So that's not a very satisfactory answer. So even if the class of effects is not commutative, if the actual effects that F might yield and the effects that G might yield do commute, then you can still do this fusion. So imagine F working on mutable state, G working on mutable state. Mutable state is not commutative, but F works on the left-hand components of a pair that's the mutable state, and G works on the right-hand components of the pair that's a mutable state. They will not interfere with each other. They will commute in this, according to this equation. And in that circumstance, this traversal fusion theorem applies. So in particular for us, when the class of effects is multi-phase computations, and the F says do things in phase 1, and the G says do these things in phase 2, those will commute. So if I tell you do X now and do Y later, that's the same as telling you do Y later and do X now. You will, either way, you will do X then Y. But my specification of what you should do will commute, even though the execution will not. So how can we capture this distinct phases thing? And the trick is what's called day convolution. So F and G here are think of them as applicative things, classes of effect. So this is a DFGA is a representation of two-phase computations. The first phase will do some stuff and get effects of class F. The second phase will do some stuff and get some effects of class G. Now to make it a functor where you've got different things going on here, there's a trick that says, well, let's pair that up with something that takes an AB pair and produces a result of type C. It's now trivially a functor because if you've got one of these and you know how to turn C's into D's, then you make one of these with a D instead, because you just stick the C to D function in the post processor here. So that's called the Koyoneda trick, parceling up some complicated gadget with a post processor, a simple post processor, and then you can do simple things to it by doing them on the simple post processor.
Why is it called Day?
Why is it called Day? Because it was invented by somebody called Day. And it's called Day convolution because it's something to do with convolution in the sense that goes over my head. It's a category theory paper from 1970. But yeah. And if F is an applicative functor and G is an applicative functor, then DFG is an applicative functor. So I can think of this as a class of effects. So I'm going to use that for my two-phase computation. So if I've got something that returns a result of type A incurring effects of class F, then I can make it one of these two-phase things that just skips in the G phase. So this is the I haven't shown you this, but this is the pure unit for the G phase, and then I've got some A's from the F phase, and I post-process them by discarding the units. And similarly, if I've got a G computation, I can make it into a two-phase computation with a trivial first phase. Crucially, the phases commute. So to do X now and do Y later is the same as do Y later and do X now, as long as you post-process the results properly. And if the two classes of effects are the same, do X now and do Y later, and they both collect effects in the same applicative functor F, then I can just run them one after the other, and I'll get something that's again in applicative functor F. So for example, this is the applicative funny apply, but discarding the left-hand argument, which is fine here because it just returns void. In phase 1, say hello. In phase 2, say world. Off you go and do it. It says hello world, as you might expect. In phase 2, say world, and then in phase 1, say hello, and then go off and run it. You also get hello world. Those two things commute. And you can even interleave the bits. So phase 1 hell, phase 2 world, phase 1 low, and again you get hello world. So this is the meanwhile back at the ranch. You can tell part of this story, then go off and tell the other story, and then tell, the things will come out in the right order. So I think this is a bit like literate programming. So this was what Knuth came up with to, well, he had this story in 1984, I think, paper in the Computer Journal, and then a whole bunch more papers that were collected in a book saying if we want to have good programmers, we should be talking to them, explaining to them how to write good programs. We shouldn't just say, here's the syntax, off you go and do it. We should say, here's a good program and here's why it's a good program. We should narrate it, explain it. We should write essays about programs. And lots of us do this. But in particular, he was thinking about writing Pascal programs, and the original version of Tech was written in Pascal. And Pascal is a very restrictive language about the order in which things must be stated. So it has constants and it has type declarations and variable declarations in it. And in a Pascal program, you need all the constant declarations need to come before any of the type declarations, and all the type declarations before any of the variable declarations. That's to allow a one-pass compiler, which was important in the machines of the late 70s. But you don't want to write your program like that. You've got one data structure that's got some constants and some types and some variables, a table of some kind, and then you've got another data structure that's got some constants and some types and some variables, a tree of some kind. You want to say, here's my table, blah, 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 blah. Here's my tree, blah, 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 blah. Now put them together into a program, get all the constants and all the types and all the variables, and the order in which the compiler sees things is not the order in which your essay presents them. So that's very much like the argument I'm trying to make. And similarly also, you might see this in program generation, metaprogramming frameworks like Halide, which is, you're not supposed to read this, there are just to show you there are some pretty pictures. Halide generates array, two-dimensional array processing code, so image processing code, by separating the algorithm, the declarative specification of what's supposed to happen, like matrix multiplication, from the scheduling, which in order to get cache coherence and so on, you need to be very careful about blocking and strides and all kinds of stuff. So you don't want to write those but all in one program. You want to say something simple about sums and products for matrix multiplication, and then something separate about scheduling. And I think that's also, I claim that as within my, the umbrella I'm aspiring to put up. So let me try and justify my points. I'm going to use, in Haskell, two monads, but the monads, they're not applicatives, but that's fine because every monad is an applicative. Retmin, the essence of Retmin, the core of Retmin, is a two-phase thing that in the first phase goes over the tree and writes out the minimum value and collects the minimum value, aggregates the minimum value. And in the second phase goes over the tree and reads from the context, and that's going to be the minimum value. So I've got one function that does this, and this is the function. In phase one, I'm going to go through the tree and write out the minimum value. And in phase two, I'm going to go through the tree and read that copy. But one of the laws about traversal is if you have a morphism of applicative functors, it will commute with traverse. What do those words mean? Well, there's transforming one applicative functor into another applicative functor in a disciplined way. That's a morphism of applicative functors. And it turns out that phase one and phase two are such morphisms, which means to say in phase one, go over this tree and do this, is the same as to say, go over this tree and for every element in phase one, do this. It doesn't matter, the phasing and the traversal don't interact because traversal is pure, it doesn't actually do anything. And now I've got a traverse with a phase one, and then a traverse with a phase two, and phase ones and phase two commute, so I can fuse those two traversals. And I have manifestly a one pass traversal over the tree. There's only one pass in the code. Then Richard's Retmin solution uses this Retmin awks with a writer thing and a reader thing, and just extracts the writer thing and the reader thing in one go, and post-processes the result, but does so necessarily using a letrec because, well, let's see here. the S that you want to run the reader on is only obtained from the writer part. So that let needs to be a let rec. But that's all you need to do to the retmin orgs to get Richard's solution. And Alberto's solution is not to extract those two things in parallel, but to extract them one after the other. So unpack the abstraction of the writer thing, you'll get an XS. Unpack the abstraction of the reader thing, apply it to S, you'll get a Y, and then you can post-process the X and the Y. And those lets do not need to be let recs. So and as lazy programs, or as Haskell programs, clearly let X equals A, Y equals B in something is the same as let X, Y be A, B in that something. What could be more equal? And so the explanation of what's going on really is this two-phase thing, this day convolution. Now you can do the same with multiple phases, and it's just an iterated use of this day convolution. So this is like the day convolution construction here. In fact, I could have used day convolution for the link. So there's a nil and there's a cons, and this is a chain of phases with some post-processing. A homogeneous iteration of day convolution. It's an applicative functor. In fact, the data type is the data type for one of the data types that gives you the free applicative, but it's not the same applicative instance I'm going to use. I'll skip over that because I haven't explained all the constructions. But so what the free applicative will do is to pair things together. It will do all the first things and then all the second things. But what we want to do, where we say here is some stuff for different phases, and here's some more stuff for different phases, you want to zip them together. You want the phase 1 things to combine with the phase 1 things, the phase 2 things to combine with the phase 2 things. And then you can inject a two-phase thing into a multi-phase thing. You can inject a thing into a multi-phase thing at an arbitrary phase. And you do that by having a now or a later. So again, don't worry about the code, just let the ideas wash over you. Something that's more than two phases, here's a kind of artificial thing that's more than two phases. Also in Richard's papers and Alberto's papers about the cyclic and the higher order programs, is to sort the leaves of a tree. So one pass, you go over the tree and collect all the leaves, that's the list. Second phase, you don't touch the tree, you just sort the list. And third phase, you go over the tree again and distribute the elements from the list across the tree. And then you'll have a tree with sorted leaves. But you want to do it in one pass, not two or three phases. So this is the program. In the first phase, you collect all the elements. The second phase, you don't traverse the tree, you don't touch the tree, you just sort the things that you've collected, and then you traverse the tree again. But you can do the same kind of calculation before the phases commute. So let's put the modify sort in phase 2 at the beginning. Then we've got phase 1 traverse and phase 3 traverse, and they'll fuse into one traverse. And so you've got this program down here, which is manifestly a single pass because there's only one occurrence of traverse in it. And that will sort the leaves of your tree in a single pass. And here's the breadth first traversal, the other story I left you with. Here's the traverse I gave you, the depth first traverse I gave you, except I just called it DFT for depth first traversal here. And all you need to do is stick a now for the root label and a later for the children, and you'll get breadth first traversal. It's only a matter of aligning the phases appropriately. So I have a whole bunch of complicated earlier programs over the last 25 years for breadth first traversal. This is much simpler than any of them. I just thought I didn't know about applicative functors then. So what has all this got to do with anything? As I said, it was the Haskell paper, Lindsay and Gan, and your co-author, who I can't read in the picture. June, thank you. Made me think, well, can I do the same kind of thing? You use free monads for representing the global program, and then you just kind of parse those free monad things in different places, different ways for different locations in the network. So endpoint projection is a matter of taking the free monad program and saying, well, what does the client do? What does the server do? They just interpret this common program differently, and that's very sweet. But I think it's doing a phase distinction. So what's different is the things I've shown you. There's a phase 1, there's a phase 2, there's a phase 3. The phases are indexed by natural number. In retrospect, I should have gone 0, 1, 2 rather than 1, 2, 3. But there's nothing inherent about the numbers, and I'm not doing any arithmetic on the numbers. And I might as well have phases indexed by location, I think. So there's a phase for the client, and there's a phase for the middle tier, and there's a phase for the server or whatever. And I say, here's what to do for client, middle tier, and server, and then here's some more stuff that happens on client, middle tier, and server. And the whole thing is put together. So, I mean, whether it's tiers or whether it's parties in a distributed message protocol, I conjecture that would all work. As you saw with the retmin, you can use monadic things in a given phase. So you can do monadic things in. I had the reader and writer monads. You can have monadic things in phase 1 and monadic things in phase 2. That's fine because every monad is an applicative. You only get an applicative structure, but I think that's this was a question that I would have asked if Alan Jeffrey hadn't already asked it after your talk, Gan, about the dynamic versus static. And I think, correct me if I'm wrong, in Haskell, the endpoint projection happens dynamically, and earlier parts of the protocol of the choreography might change what gets projected, which gives you great flexibility, but seems contrary to the spirit of endpoint projection. And it's not how everyone does endpoint projection, I think. So the book by Fabrizio Montesi has endpoint projection as a separate phase. It's something that happens statically, and this doing it with this deconvolution multi-phase thing, I think would give you transparently a static division. And then I think Alan also asked about conditionals and the selective, applicative, and so on. So maybe I'd love to keep talking. So I'm going to conclude. I did, in fact, use my time. There's a paper from Maths of Program Construction 2022. It's joint work with Ashim Kidney, Tom Shrivers, and Nick Wu. And I encourage you to read it. It's on my webpage, or it's open access at Springer. I think choreography is an applicative thing, and I think this deconvolution, this multi-phase thing is the way of capturing it, and multi-tier stuff and so on.
We can do one quick question, I think.
You said that phases could not be numbers, but something else,
right,
like locations. But the phases are ordered in somehow.
Well, if I'm going to want to run them one after the other, then I need to say what order I'm going to run them in one after the other. But if I don't want to do that, I don't need to do that. So if I say there's a client phase and a server phase, and then I end up with this thing with something for client and something for server, I need to then extract the client stuff and the server stuff, and I just say, well, the client stuff goes to the client, the server stuff goes to the server. And then hopefully, I mean, as in a choreography, they will run concurrently, not one after the other. So I can use natural number indices to schedule these one after the other, but I can use location indices to schedule them by distributing them to different sites. So it doesn't have to be one after the other.
Well, we can do one more.
You baited us by saying that maybe this is not really one traversal, but you won't go into it.
Yep.
Was it a debate that you want us to ask you about, or?
Well, I mean, I think it's indefensible that it's really saving you anything, and it's actually very obvious in Alberto's program that what you construct in a single pass is the minimum and a function. And that function is a closure that contains all the structure of the tree because it's something that takes the replacement label and gives you a whole tree. So now I give you the replacement label, you have to unpack it to a whole tree. So, I mean, you're not traversing something, perhaps, but you've still got a whole tree's worth of stuff to do.
Is there a solution where you're not creating a hidden tree?
Well, I've argued with Nick about this and what's actually going on, and you write it in different ways. I mean, it just messes with my head. I don't know what's going on. So you might say you end up with one pass over the tree, you get the minimum, and lots of shared pointers to the same. In the same pass, you make a new tree that has lots of same pointers, shared pointers to the same thing, and then you just fill in that thing like a logic variable. Is that actually what's going on? Well, I deliberately don't think about those questions. I have no operational model, really, of what's going on with my Haskell code. I deliberately have an equational model, and I can only stay sane by only focusing on the equational model. And then Nick comes and has an argument with me and says, no, it's not doing that. And I think, oh, poof.
If the spine of the tree is strict, right?
Yep.
In the lazy version.
Yep.
And you just have a lazy cell where the
Yep.
minimum goes, then I think you can get
Right.
away with
I certainly think you can get away with that. Whether these programs actually do that, I don't know.
Yeah. All right. Thanks. And there's a break now.
we'll create, and then he took my request to write things up seriously, right? To things it seems that we know or we have known or we should have known for a long time, but that just never got properly written up. Anyway, so take it away, Will.
Hello. Woohoo. Just to repeat, I'm Will. Nice to meet you all. So, this talk begins with a very simple question. Where are all the functional programming design patterns, bracket closed? In fact, this question was asked 12 years ago on the Software Engineering Stack Exchange, as you can see. Specifically, this person asked, OO programming literature is full of design patterns. Most books on object-oriented programming dedicate a chapter or two to design patterns like factories and decorators. So what are the equivalent patterns in functional languages? Why hasn't anyone written a book about them yet? Is there something special about functional languages that obviates the need for design patterns? Which, I mean, I think these are all really interesting questions. They were on my mind. But you'll never guess what the top answer is. Jeremy Gibbons is writing the book. So, Jeremy? All right, so the book is still being written. That's OK. But in the meantime, while Jeremy's been writing the book, several other people have also decided to fill in this void. You can find now published Scala design patterns, Haskell design patterns, Scala design patterns. They're not very creative. Functional programming patterns in Scala, Scala functional programming patterns. But OK, I have skimmed these for you, so you don't have to. And these books don't feel like they capture the essence of what made the original design patterns so influential. They tend to do one of two things. Either they translate the original design patterns into a new language, like Scala or Haskell, or they tend to explain standard library types. You know, a monad is a burrito, that sort of thing. And so to get to the heart of my question, why do I feel like these aren't really the successor, the functional successor to the design patterns? We have to ask, and I was asking myself, what is a design pattern? What is its purpose? And I'm going to give you two perspectives on this question from the old times. The first one comes from Peter Norvig, who said that design patterns are descriptions of what experienced designers know that isn't written down in the language manual. So this is an important idea. There's a term called tacit knowledge for things that experts know but they have trouble articulating. And I see the role of design patterns as articulating tacit knowledge in a shareable form. And Peter gave examples of tacit knowledge like how to choose classes and methods, abstractions for program organization, discussing design trade-offs, avoiding limitations of the implementation language. All good examples. And so this is a useful perspective, and I also want to go back to the very source. For those of you who don't know, Design Patterns is a book written in 1994 by a group of 4 computer scientists, collectively called the Gang of 4. They wrote a book called Design Patterns with the following purpose. They said their purpose is to record experience in designing object-oriented software as design patterns. Each design pattern systematically names, explains, and evaluates an important and recurring design in object-oriented systems. The goal being to capture design experience in a form that people can use effectively, so they wrap them up in a catalog. And the thing I want to emphasize is this second sentence here. Right? First, this concept of systematic naming is important. If I share all of my experience with you in a huge monograph, it's not indexable, it's not shareable in small pieces, but names give us vocabulary to talk about systems at a higher level. And additionally, this idea of important and recurring designs is really essential, because to me, what distinguishes a design pattern from something like, say, a functional Perl is it's not just an insightful or clever way to organize your code. It is something that has been repeatedly proven to be useful in real-world applications. And so to recap, I think a design pattern should, 1, capture a recurring phenomenon in real-world system design, and 2, provide a software design strategy for managing this phenomenon that is difficult to describe mechanistically. And I think these criteria can help us start to see why functional design patterns have been historically elusive. For the first criterion, it's somewhat straightforward. There just aren't that many real-world systems implemented in functional languages. Or at least the fraction of code in functional languages is dwarfed by orders of magnitude by object-oriented languages. And so we just don't have that much data. But even if we had the data, there's still a question: what kinds of phenomena are difficult to describe mechanistically? A common criticism of the Gang of Four patterns is that they arise in part due to the inexpressiveness of the implementation language, like C++. And in fact, Jeremy wrote a great paper about exactly this called Data Type Generic Programming, and there's a wonderful quote: "The origami approach to data type generic programming offers a good way of capturing precisely the essence of a number of the Gang of Four patterns. This is appealing because, without some kind of data type generic constructs, these patterns can only be expressed extra-linguistically as prose, pictures, and prototypes, rather than captured in a library, analyzed, and reused." So I think this quote gets to the heart of it, right? With a good enough static type system, or with a dynamic type system, which was what Peter Norvig was advocating, you can take ideas like a visitor and make them fully linguistic abstractions. And the abstraction itself still needs documentation, but the point is that the abstract idea behind the pattern moves from the realm of prose to code. Which, at that point, sort of begs the question, is the visitor still a design pattern if it's just a library? If we say yes, that seems to imply that any library is just full of design patterns, which kind of dilutes the term to a point of meaninglessness. And so returning to my criteria, when I ask where are all the functional programming design patterns, my thesis is that we need to do two things. First, we have to find a source of systems implemented into functional languages across a variety of domains. That's going to give us fodder to find recurring phenomena. And second, we have to revise our understanding of tacit knowledge used by expert functional programmers to build systems. When the language provides support for sophisticated abstractions, what then becomes the hard part of system design? And so in the rest of my talk, I'm going to give you my answer to these questions, but I want to put a pin in this because part of the goal of this talk is to discuss these questions, right? This being the inaugural Fun Arch. Great place to talk about this. And so I encourage everyone in the audience to reflect on your own experience. What is your conception of a design pattern? What is your tacit knowledge about functional programming that you think others may not have? We'll talk about it after. But for now, I'll lay out my perspective. So to start, where can we find a large range of systems implemented in a functional language? Well, for anyone who knows me, this is an easy guess to make. It turns out there's a functional language being widely used today to design robust, high-performance systems in a ton of places. Hey, it's Rust. Okay, now some of you skeptics might be thinking, well, Rust isn't a functional language, okay? But I think it's useful to think of Rust as being functional. It's expression-oriented, it has closures, generics, first-class functions, immutability, type-level programs, and traits, which I think are the most interesting aspect of what makes Rust design distinct from object-oriented languages and similar to languages like Haskell. And so, of course, there are other functional languages we could look to with moderate industrial usage, like Clojure and Scala. I just don't know those ecosystems as well. I've been programming in Rust for about 8 years. That's my expertise. That's where I'm going to focus in this talk. Now, the second question, the second criteria, is a little trickier. What kinds of knowledge should be articulated as functional design patterns? So here's my take. In programming, you have dozens of application domains, right? You have web servers, game engines, numerics, compilers, and so on. And when statically typed object-oriented programming became popular, it offered a relatively small number of core language mechanisms with which to model the phenomena across all of these domains, especially at the time the original design patterns work was done. Everything had to be boiled down to an object. Most forms of reuse were inheritance. Code was made generic through subtype polymorphism mixed with dynamic dispatch. And the design challenge then was to do a lot with a little, to model everything with a small number of load-bearing types, which required a lot of cleverness that got articulated as design patterns. But in the FP world, it's a different story. We have so many more modeling tools at our disposal, right? You have sums, products, modules, references, lifetimes, traits, closures, you name it. And this changes the nature of design, because now you have so many tools, it can be hard to know which is appropriate for a given problem. And so I think one role for functional design patterns is to take a common phenomenon in system design, right? Something that occurs in many of these places on the left, and gives guidance on how to find a good encoding into the right subset of the many mechanisms you find down here in the bottom right. And especially when we focus on static typing, good encoding usually means things like user mistakes are caught at compile time rather than runtime. We've effectively encoded properties and invariants into the type system. And so to demonstrate that, I wrote down in the paper 4 different design patterns that I've seen in Rust. The witness, the state machine, the parallel lists, and the registry. Each design pattern describes a mapping from some domain pattern, like state machines, into a configuration of type-level mechanisms, like phantom types or modules. And I did not just make these up. Each pattern can be found in multiple widely used Rust libraries that are sourced in the paper. And now to illustrate further, I'm going to take one of these patterns, the registry, and walk you through it for the rest of the talk. You're going to learn about the specific design pattern, but again, my goal is not just to teach you about Rust. I want to argue this is representative of a way we could, in general, articulate functional design patterns. So let's get to the code. All right. So the event, again, the pattern we're going to talk about is the registry pattern. And this can be seen in a number of domains, like if you're doing dependency injection. And the case we'll talk about today is event systems. So the basic idea is you have some kind of events structure, like this, that's going to hold events. And there's going to be 2 key methods we care about. One that registers callbacks f on events. It's going to have some kind of event name, which is a string. And then it's going to have some kind of data, or some kind of function, f, which is going to register that function. And then we're going to trigger callbacks given some name. So an instance of how we would use this API would be if we say let mute evs equals events default. Then we want to, for instance, register something. Register for the click event, something like print line, I've been clicked. And then we want to trigger this, again, with click. And that should cause some behavior to happen. We need to add a derived default up here. And I'll try to explain some of the relevant Rust syntax if it gets super gnarly. And so we can run and compile this. Right now, it doesn't do anything because we haven't implemented the functionality, but we have the skeleton of our basic implementation. And so the simple way to do this is we need some kind of listeners map that's going to map, hash map, that's going to map from a string into a box dyn listener. So a listener is the type of things that we can call as listeners. And that's represented, normally you would write out function types with arrows in most functional languages. In Rust, you have to use a trait, because that's the way you correctly abstract over things that are both raw, like plain functions and closures. And then this box dyn thing is a way of doing dynamic dispatch. Oh, sorry, this should be a vec dyn box. Because we want to have, if we have a heterogeneous list of many different functions, then the common thing amongst them is they implement the listener trait, and otherwise we abstract all other details. So the way we could use this is say self.listeners.entry name .or insert with vec new .push f. All right. .push box new f, putting that on the heap. And then when we trigger it, here I'll give a little more space for the type annotations. When we trigger it, we say let's get out the listeners if they exist, self.listeners.getName. And we're going to say for f in fs, call f. All right. Oh, we almost got that, except we have to declare that this is a listener. And now we run this, and our previously not working example works. It says, I've been clicked. Again, just to briefly pause, remember, the point here is this is how I think we should be illustrating design patterns, right? You sort of iteratively build up functionalities in small self-contained examples, and you need to be talking about encodings into the different types that are relevant here. And so, for instance, this is not, we have to talk about expressiveness as one dimension of these designs. This is not an expressive event system because our events do not take parameters. They need to have some kind of payload that is unique to each individual event. So the way that we'll represent that idea initially is, let's say we have a finite domain of events that we've decided ahead of time. We can represent that as an enum. So an event could be either, say, a click event, which will have an X and a Y. We could have a key press, which is, say, a char. And then a listener now takes a pointer to an event. And all of this is the same except the trigger function, where now we need to take as input some data that we pass as input to the function. And now down here, let's turn off company mode because it's getting in the way. Now down here, we're going to take as input that data and match on it and say if we get an event that's a click, we can print that out, X and Y. And if we get anything else, that's an invariant violation. We don't expect to receive any other kind of event when registered for click. And then similarly down here, we can pass as input X is 1, Y is 2. And let's see if I managed to type everything correctly. Almost. 36. I am missing expected operator. Oh no. What is happening? Sorry. The extra semicolon. The challenges of live coding. I'm totally duffing this up right now. Sorry. Let's ask Rust to tell us something useful. Oops. I missed the thing we're matching on. See, this is the challenge, to get all the details right live, but luckily it doesn't take us too long. All right. So let's go back here. Now we've matched this, we're running it, and we've successfully executed this. And so this is decent, although it's still, obviously, you're starting to see the bones of why this particular encoding is not desirable. Because when we match on some data, there's some possibility that we might get the wrong kind of event. Or if we typo either the event names in the trigger or the register, we could send data to the wrong place. Moreover, this is also still fundamentally inexpressive on some level. It is a closed system that cannot be extended with a new event type. So an important question is, how would we make this extensible if anyone wanted to add their own kind of event? So the way we do that in Rust is essentially, first, you're going to take all of these things that were previously part of an enum and make them distinct types. So you have a struct that's a click. You have a struct that's a key press. Delete the event. And then instead of taking as input a specific type, we just say we take any type. And this is coming from the standard library. It's a trait that basically says this thing is dynamically typed. And the only change we have to make now down here is instead of matching on an event, we have to explicitly say downcast ref and then cast it to the specific type that we're expecting. And that will give us back an option, either containing the type that it is, or we get back a none if it's some distinct type. And then event 13. Oh, right. And then this also needs to change to dyn any. And type. No, you don't. All right. So now, again, we get the same functionality, but we've extended this into an extensible system. We can pass any kind of data here when we trigger the thing, and then we match on whatever data we expect to get back. So that's nice. But once again, this is still deeply troublesome because there are so many ways we could mess this up. And also, this is a ton of boilerplate to have to write every single time you do a match. But this is roughly the system design you will find in places like JavaScripts, add event listener, have something that looks like this, just fully dynamically typed, so they can hide many of these type conversions away. All right, so the core of the design pattern I'm going to communicate is how you can unify the concept of this key with the thing that it is meant to correspond to, in this case being the sort of event payload. The insight is that when we're talking about this kind of callback should only be registered for the click type, and so the type itself can represent a key. And the way we represent that idea in Rust is first we're going to need this type ID structure. And we're going to update a few of our type definitions. So instead of a listener on any, we have a listener on a specific parametric type E. We have a vector of listeners now, vector of box dyn listener of E. And then this is going to get updated to box dyn any. And the key thing is now, rather than having an event name as the key to the hash map, you have a type ID, which is the type of events that these listeners are listening on. So this is sort of it's a little bit indirect, but it's a sufficient encoding to give us the extensibility we want without having any sort of other imposition, or without having this sort of disconnect between the keys and the values. So the way that we update our type signature here is now we have some event type E that is tick static. You can ignore that part. We can get rid of the name, because that no longer matters. F is a listener on E. And now when we say .entry, rather than passing in name, we pass type ID of E. This being the key thing. The index into our hash map is the unique type of the event. We get back, then we have to do something a little fancy here. Box new, listener vec E new. All right. Then we have to downcast that, downcast mute, listener vec E. Because now we have this dynamically typed data that is directly referring to the vector. And then we push our function into that. Oh, and we want to unwrap that. And then now down here, when we trigger the event, again, this is now parametric over some event type E. So we can delete the name. The data should become exactly that type that we're asking to call an event on. And now we have to, again, do some kind of downcasting. So we say fs.downcast_ref listener vec of E dot unwrap. So now we've said we're specifically listening, we want a vector of listeners that are specialized to the type E. And finally, when we want to update our API, we can just start deleting stuff. We can get rid of this. We can move this click pattern match up into the type, the argument list. And then get rid of all of this. Wonderful. And we no longer need the name when we trigger this either. Now, the moment of truth, who thinks this is going to compile after everything I just typed? Oh my God. Got a name. That's right. All right, we also have to index on the type ID of E. All right, that was the only thing missing. So this is pretty cool. With this new interface, we've now unified the key, the name of the event, with the data type that it's meant to correspond to. And the nice part about that is we just have to specify somewhere in the definition of this closure what the type of the payload is, and the type system takes care of the rest. And importantly, when you're talking about communicating these design patterns, you have to articulate the things that one can no longer do, the user failure modes that now became inexpressible, which in this case are, I cannot, for instance, trigger a click callback with a key press event. So if I replace this with key press C space or something like that, then as you expect, nothing runs, and there's no sort of hack within the system to convince Rust that click and key press are the same thing. Now, of course, this is not necessarily a perfect system, and there are important trade-offs to designing things this way. Like, if I accidentally make this type weirder than I expected, for instance, if I made this sort of a reference or like an RC, and I made the types not literally unique, there are certain ways I might shoot myself in the foot and then not realize that I was registering an event for a different type than I expected. So you still have to be a little bit careful, and it's possible that you might sort of register something for the wrong type and then just never have your event get called, but you'll never have these sorts of invariant violation failures. That's the promise of the registry pattern within Rust. And again, there's a similar idea where if you use dependency injection and you ask for specific types, you can make sure you only get correct values of those types. And you can see there's actually several different implementations of this kind of pattern within the Rust world. So let's bring back up the slides. There's my tweet. And then I think, there we go. Right, to emphasize that this is a pattern, you can find a version of this in the Matrix client, which is a chat server that uses these extensible event contexts. You have the liquid string templating language, a version of that written for Rust, that uses a plug-in mechanism where you can add arbitrary features to the language using this construct. And then when you have games like Bevy written in the entity component system architecture, they use a similar kind of idea to have this global map of like global mutable state for the game. And you can say, I'm going to get global mutable data of this type or global mutable data of this type. And you can fetch those independently of each other from this central store, which has almost an identical hash map structure. All right. So that's pretty much what I wanted to say. Again, the high-level idea is, what is a functional programming design pattern? I hope I've given you some food for thought on the principles that should guide that, that idea of coming up with a definition of a design pattern. I've shown you one specific instance of what a design pattern could be in the context of Rust. And finally, I want to wrap up by having a great discussion about all this. So here's the way I actually want to structure this, especially because there's a lot of you, is I'd like everybody to find your 5 closest friends, and we'll do a little roundtable small group discussion, and then you can all ask me or tell me something interesting that you discussed in your groups. So here are some great questions to get you started. Of course, you can talk about anything. Like, what are the qualities of a good functional design pattern? Or do you have specific good examples that you like? And if we were to truly construct the successor to the Gang of Four's design patterns for the functional era, how should we do it? What are the elements of that construction process that should be considered? How do we find these good examples? So that's my talk. Let's get discussing. Thank you. So let's take, I have 15 minutes, I believe. Yep, so let's take 8 of those minutes to do small group discussions. So again, just find your 5 closest friends. Talk about these questions with them. And then you can, I'll be there and we can talk at the end. Go for it. All right, everyone. Let me get your attention for 1 second. This is amazing discussion, and I love it. We have 2 minutes remaining until we have to swap to the big group. So what I want you all to do is pick one person who will share one thing. It's either a comment of something interesting that you want to just share with the group, or a question. You can ask me, and I will respond. So 2 minutes, figure out what you're going to say. Go for it.
Is this working?
All right, all right. Everybody bring it back. Everybody bring it back. Focus, focus. We are now returning to the collective unconscious, the group mind. That's where we're all at now. So, who would like to volunteer to offer a cool fact or question? Thank you.
We think that in Haskell, at least, we already have design patterns in form of type classes in base, like traversable, like monoids, semigroup. They're used all around. State monad is also like this. They form your code. They're used everywhere.
Yes.
And enforced statically. It's similar, for example, you have observable design pattern. It's on the same level of abstraction, like traversable, for example. It's similar, like a level of abstraction. That's our comment.
Amazing. Thank you. Yeah, that's a great point. And I think this is an important question. When is an abstraction a design pattern, and when is it not? Because again, I will just comment on that. My sense is I think we should not consider those abstractions to be design patterns in like a, you can get definitional about this in a way that's not useful, but I think the point I'm trying to make is we should redefine design patterns to be the kinds of knowledge that cannot be encoded as those things. Like once we have something that's a fully linguistic abstraction like that, that's great. Now we have an abstraction. And design pattern is now everything that's left. That's how I would say it. But I think these are both totally correct viewpoints and consistent with how people use the phrase in practice. So I think that's an interesting tension. Hans, yes, please.
So John Valsides was right with you. I wrangled with him many years ago, and he told me if it could be formalized, it's not a design pattern.
Okay.
So we have a lot of questions. What's the difference between a design pattern and a tip or a trick? So we came up with a couple of tips and tricks, like write combinator libraries, or if your problem has a sequential composition, consider writing code that uses function composition. Are these design patterns, or is this just things that experienced designers know that aren't in the manual? We don't know.
Right. Yeah, great question, or great point. And to me, I feel like there's something about a pattern that evokes the notion of a template. There's something of, and this is something I bring out in the paper, and I don't talk as much here, is that there are distinct like abstract elements. So in the concept of the registry, you have like the key and then the requests that are keyed on that key. And you can identify in every instance of the pattern, whether it's event systems or dependency injections, a mapping from the abstract variables, abstract sort of schematic pattern variables into the concrete instantiations. And that to me has the essence of a pattern. And whether that captures the examples you're proposing, I'd have to think about. But my thoughts. All right, in the back.
So I thought that was a really interesting and eloquent way to put it. If it can be formalized, it's not a design pattern. And one thing we were talking about is if we were to forget all the knowledge we currently have of design patterns, would the same ones reemerge later? Like, are design patterns discovered or invented, essentially? Yeah. And I think if they reemerge later, they're probably more formal, like the applicative laws or something like that. But it's not necessarily the case that we would rediscover the flyweight pattern or something unless we happen to run into the right conditions.
Yeah, great point. You want to mention? Yeah, go ahead.
Yeah, I think we discussed I think there's one, just like Sean mentioned, there's one thing actually quite common in the industrial settings, really like we actually do a lot of large-scale data transformations. So you kind of like really design a data pipeline from just like a different paths in compiler. You really have transformed this data from multiple stages. And that's actually quite common higher level architecture pattern, I would say. And it is not particularly articulate, but I've seen a lot. So it's kind of like, oh, that's one thing. The other kind of we can discuss really like, because in my company, I'm doing their basically static analysis. When we using different tools, if I use another C++ code, I use clan. Obviously, I'm going to use the AST represented in the object-oriented type hierarchy. You're going to use the wizard pattern to do this thing. and that's a standard design pattern in OOP world.
Yeah, yeah.
But if I use functional programming, then I use expressing ADT, then it's pattern matching, which is very straightforward. And do we call this design pattern? This is obviously a language feature, a very prominent language feature in functional programming language, right?
Right.
And it's really like in OOP language, you cannot, or you have to represent your object syntax tree or algebraic data type via OOP design.
Yes.
Then you have to have this visit pattern to achieve the pattern matching.
Yeah.
Right. So that's kind of like, yeah.
Right. Yeah, no, fabulous points. And I think this issue also of granularity is super interesting because both the original design patterns and the ones I'm talking about are sort of like very fine-grained code and distinct from like the hexagonal architecture, these sorts of things we've discussed.
Hi, thanks for provoking us, Will. I'm going to agree and disagree with John Vlacides. So if it can be formalized, it's not a pattern. Fine, that's good. But if it can be formalized, then that's not all of the pattern. What you formalized is the formal bit of the pattern, and the pattern is all the tacit knowledge that goes along with that.
Right.
And that was the obstacle I had when I tried to sell this data type generic programming thing as this is what patterns are to the OO people, and they said no, it's not. We've missed out all the other stuff, which I think is fair enough. So traversables was mentioned. The paper by Conor McBride and Ross Patterson that introduces this is great because it does the formalization. It says here's the construct, and it doesn't leave it there. It goes through and explains a whole bunch of applications of it and things that you might not have noticed the first time you see the piece of code. So that's unpacking the tacit knowledge that they had, perhaps if you like, and making it explicit. So and that's a great paper, and I think I've come to think that the functional programming equivalent of design patterns is papers like Functional Pearls. They capture a lesson, a fact. It might not be a new fact, and the fact that's taken as a point of honor in the design patterns community. You don't invent patterns. You have to mine them from existing stuff, otherwise you're just fabricating things. It doesn't count. So fine, doesn't have to be a new idea, but giving it a name so that people can use it, and telling the story around it so that people remember it and can see how it will fit into their context. That's all part of the pattern, and I think our way of expressing these and recording these is things like functional pearls.
Yeah.
So. What are the qualities of a good functional design pattern? I think they pretty much coincide with the qualities of a good functional Perl.
Okay. Well, it's a great perspective to end with, because I think we're out of time. Move on to the next one. So thank you all again for your wonderful comments, and I hope this is thought-provoking beyond this session. We can continue to talk about this.
Is Ivan Perez, who's also going to talk about typed patterns. I think his fourth paper / talk that he has at this event, right? You got one at ICFP and 5. I'm sorry, 5. Okay, so.
1, 2, 3, testing. All right, let's go. So let me. All right. Well, thanks everyone for sticking around. My name is Ivan Perez. I'm a contractor at NASA Ames, and I'm here to talk about a little pattern that I kind of saw, and I don't claim to have been the first. At least, in fact, I know I have not been the first to see this, and I know that there are libraries that allow you to work with this. But it's something that it's been recurrent in my work, and I thought I would write it up and also tell you a little bit about how we're using it, and maybe we can have a discussion. I know that there are bits about this that I don't understand, and there are people in this room who are smarter than me and know more about it, so maybe you can help understand what's going on with this little pattern here. So the story is this, and we're writing a compiler of a language, a stream-based language, and we want to generate C. And I'm picking this for reasons connected to the work that we're doing at NASA. But this could be any compiler. And presumably, when you write a compiler, you have some sort of concrete representation, then you parse it, then you process that, it has some sort of higher representation, a symbol table. Eventually, you get to an intermediate representation, refine, optimize, and you produce some target code. And at some point, you're going to have an abstract syntax tree of your language, right? In this particular language, it's a stream-based language. So you might have a constructor for constant streams that you just provide the value, and that means the stream has that value at all times. You could delay a stream by a sample, or you could apply an operation to a stream and transform it, and that operation is applied point-wise or time-wise at every point in time. And presumably, you would have other constructs. This is not the full language, it's just a toy example, right? Now, if you parse this from a file, if you parse a sentence in the language from a file, and you try to construct a tree like this, there's a chance that the sentence is wrong. Now, you could stop there, produce the error message, and you're done. And then you stop parsing. But if you want to keep parsing, then and keep producing kind of like a tree in some way, you have to fill in the branches of the tree that have failed. And you could find this useful because you want to process that tree later. You could also find this useful because you are doing something like pretty printing, where if you parse something, then you know how to pretty print it. And if there's a parsing error, you don't want to lose it. You want to keep it literally there and then put it literally in the output text. So there are different ways that you could fill in those gaps in the tree. You could put a maybe when you cannot parse something, if all you want to do is record that there was an error. You could put a string. Oh, there's a typo there. You could put an either with a string, and you keep the literal text that you could not parse. Or maybe if you can assume that the lex are actually completed successfully, you could just keep the tokens, and so on. There could be other mechanisms. So let's assume that you just put a string, the string literal. It could be the string you couldn't parse, or it could be an error message telling you what happened there, right? And this is what that tree would look like if you decorated with the string everywhere. You have an either in every place where you had content in the AST. So the constant, instead of taking an A, now takes an either string of A, so it could be an error message or an A, the same for each one of these and each one of these. There is a chance that you may want to add other information to that tree. For example, to produce sensible error messages, you might want to annotate everything in the tree with the locations where things came from. At some point in the compilation process of the tool that we built, we add types to every expression in the tree, or to most expressions in the tree. So we kind of go to all of them and we annotate it with the type, right? So what you end up with is a bunch of different variants of the tree, right? This is what it would look like if you add the locations and the types to the tree. And you see that it's kind of similar to the other, but not exactly the same, right? So there's some sort of repetition here going on. So if in compilers, it's very common that you will have this kind of multiple representations of the same tree in some way. And you can see this in the wild. This is present in compilers that are being built in the functional programming community. You could also, sometimes some compilers. I think BlueSpec is one example. And I don't want to name names, but I remember finding this, that there were parts in the AST that only made sense later in the compilation process. It's like you kind of, if you wanted to build an AST for the purposes of pretty printing, you had to put information that didn't make any sense for you, right? So either you end up with some sort of duplication, multiple versions of the tree, or you end up with a tree that gives you kind of like a poor API, I would say, because it has information that is not for you, right? So this is where the extensible type design pattern comes in. So the extensible type design pattern is a polymorphic type with a type function argument. So it's a higher kinded type. And the type function argument is applied to every element of the tree. That's it. So this is what it would look like in the example that we saw. We take an extra f and we apply it everywhere. Here, here, here. We pass it. Here, here, here. And notice that we also pass it to this guy, because this is part of our language and we want to make it available everywhere, all the way down, right? Now, of course, let's play with this guy. If we put an identity, we get the original stream. So if all we want to do is evaluate, simple enough. If we put either string, then now we can put error messages. We can put literal text that we couldn't parse. We can put this tuple function with 2 out of 3 elements, with the type and the location, and then leave the whole for the other. And then everything is annotated with a type and a location. We could put maybe, if we want to encode a notion of failure. Maybe could also encode a notion of update. For example, if you have 2 versions of the tree and you want to encode how the branches differ, you could keep only those in the second version that are different from the first, right? So you could use maybe to encode that information. And there are ways of working with compositions in type functions. So there's a library, in the paper I used type compose, which is a library created by Connell Elliott. And using type compose, you can compose a bunch of these. So you could say, well, I want to have types and locations, but also I want to encode a possibility for failure, or I want to encode, add an extra case, right? So you can compose multiple of these. I'm not going to go into compositions in the talk, but in the paper I explore that a lot. So what can you do with this? It's actually pretty funny, because it's not just that you can apply it everywhere. It's that you can selectively add information to different nodes in the tree. You can selectively add new cases. It's not just that you can add a type and a location. You can also add new cases, like we did with the either string, where everything gets a new case. You can remove branches completely. You can trim parts of the tree and say that can never occur anymore. And you can modify, because you can add and remove and you can modify, but also there are other ways to map. And when I say selectively, I want to be very careful with that word. I don't want to mislead anyone. The selection is based on the types, because we're using type functions. So you cannot selectively, like if you apply the f everywhere, you cannot later, at least as far as I know, you cannot later say, I'm going to make the selection only here but not there. Well, they better have different types, otherwise you're not going to get away with it. In the paper, the use is for compilers. The description of the use case is for compilers. But I actually experimented with user interfaces, and this has uses there too. And I think it has uses in other areas, and I'll speculate at the end, and I would like to hear if other people have tried this, because I know it's in the wild. Okay, so I'm going to show you how to do additions. Recall, this is the definition that we're working with. This is the extensible type design pattern. And now let's say that we want to selectively add, right? So we want to add information like type and location here, 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 and here, but not here. And this is actually what happens in the Copilot compiler that we use at NASA, which is operations. We know their types. We don't need to annotate it with the types, because the constructors tell us exactly the types they have. So we only annotate other expressions. Well, in Haskell, we have a mechanism to do this, which is this, with a type family. If it's an OP, we leave it unchanged. Otherwise, we put the type, and then we're done. So we can selectively decide which ones are going to have extra info and which ones will not. And now, this is not actual code. This is just to show you what it would look like if you do it, right? That if you put the carry type function there, then you have the type here, 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 and here, but not there. Sorry for the, hang on. Okay. So, you can also extend trees. Let's imagine that you have a simplified tree, and now you want to have one extra case, syntactic sugar, something that you can reduce to some other expression in the tree. In this case, a drop, a new expression. So how do you do this? Well, you add the drop, a constructor for the drop sentence in your language. And in our particular case, how this would work is that we want to drop elements from a stream. So we need to know how many elements and the stream that we want to drop elements from, right? So we define that data type. And now we create, again, a type family that says, if it's a stream, I extend it with a new case. It's either a drop or the original definition. And otherwise, I leave it unchanged. Yes, this is making noise. There we go. Thank you. And thank you. And sorry to the people on the line. You can also modify things. So for example, you could use this to modify all the ints and turn them into C ints. Modify all the doubles and turn them into C doubles. You can modify types. And another use case that I found that at least I found interesting is that before we said that we can use either to put error messages in the tree or to keep literals, and then to put the literal text that we fail to parse from a file and then be able to pretty print it and so on. But the type doesn't tell you how you're supposed to interpret the representation. It only captures the representation. And there's a cool use case that at least I found it interesting, that you could use this to extend a language without variables with variables. If you interpret the string as a variable, then you have a language, and suddenly you can add variables everywhere. Which means, like, if you're familiar with languages like, mustache, PHP, these kinds of things, they allow you to include one thing inside another. So you could do this trick here and put an either everywhere, and now you have variables everywhere. And you would, of course, have to traverse it. This is the concrete version of the tree. This is not the extensible type. But if you put the either in the F, as we saw before, then you would end up with something that is like this, right? So the either, if it's a left, it would be the name of a variable. If it's a right, it would be a concrete expression. And this is an example of what a particular sentence would look like. So in delay, you could have the first argument would be, oh, actually, this should have been a number. My mistake. This should have been a number. Right of a number. And on the left side, you have a variable name. So this is kind of like a construction that will take a variable and delay it by one sample, right? Oh, no, delay is right. It was drop that had the number. Sorry. Now, you could say, why not just put the variable here as an argument? Like, it should be the same thing, right? But there's a benefit to doing this, that you can serialize it. If you do this, you can print it, and you could read it. So you could read it from a file, and you could, so there's that benefit. And this means you can take a data type, use the extensible type design pattern, and suddenly you can embed things in it. And it's not just that you can add variables, you could add expressions in some other language, right? So I'm actually going a little bit fast. So any questions so far? Comments? Complaints? No. Okay. Yes?
This is something she the microphone, please.
Microphone.
This seems to be something that GHC has used to deal with some fields using type families depending on which phase of the compilation pipeline you are. Do you have any thoughts about what are the main differences between this approach and what we can find there?
I'm not an expert on GHC. I had a discussion with someone from Galois when I was during the rebuttal of ICFP for this paper. And then they did mention that GHC used something like this, but I would like to hear from people who work on the compiler to know the differences. Like, if it's exactly like this, or if they're only to add information, or only to replace information, or anything like that. And also, you found any limitations, like if there were cases when you wanted to do things and you thought this is actually a bad idea. Well, yeah, you can go ahead. We are actually running a bit faster, so I don't mind like having the discussion now. Sure.
So yeah, so in I'm Richard Eisenberg at Jane Street. So what GHC does is quite similar to what you're describing here. The difference is that at each, so go back maybe to a slide any slide with there. That doesn't matter which.
Yep.
Well, no. Sorry. Doesn't matter which version of the ADT. That's a fine one. Yeah. So here we have const delay and apply.
Yep.
The F takes like a little symbol that either says const or delay or apply. So instead of just doing type-based disambiguation of like whether you're adding or removing or whatever, you can actually have, yes. So in both const and delay, we see that there's FA. Maybe we want the const node to add something to that FA. But we don't want it for delay because in const it would be like F const A and delay would be F delay A. We can case on whether it's const or delay, and that way customize per constructor. Other than that, it's basically this idea.
Mm-hmm. Yep. All right. So I'll tell you a little bit more about how we're using this. So at NASA, we have a runtime monitoring language. It's called Copilot. And I think you may have heard about this already throughout the conference. And Copilot has multiple representations of the AST. It has the Copilot language representation, which has almost no information. And then it has the Copilot core representation that has type information, but also doesn't have some of the cases that exist in the original tree. And at some point, the compiler transforms one into the other, so you have to work with both. And then we have another tool that we use to generate like ready-to-run monitoring applications. And the idea is that you write some high-level spec, hit a button, and you get something that is ready to deploy in a flight system. And for that the tool that does that is called Ogma. And Ogma generates, as part of all the content it generates a Copilot specification. And for the requirements at NASA, we need to have traceability from the high-level spec down to the code that we generate. And that means we don't want to generate just a Copilot AST because we need to annotate the expressions with information about where they came from. So we can't use the same AST anymore. But with this, we can add information to the tree. And now what we have done is rewrite Ogma to use these techniques so that we can use the same AST for the low level, mid level, and high level in Copilot. Now, it's not clear to me whether conceptually the internal core representation in Copilot should be the same as the high level one, even if they happen to coincide. Maybe they just, they should be different regardless. But we could do it, like we can do it. And definitely the high level in Copilot and the one in Ogma should be shared. By the way, a little bit of publicity mode on. These tools are open source. You're more than welcome to go to the repo and check them out and try them. And if you find bugs, file them. And they see releases very regularly, like every 2 months on the day. Like we have never been late in the last 2 years, even by a day. Like we're very thorough on this. And so the what we have found is that we can reduce the number of representations of the tree from 3 representations down to 1. And with that, it's not just the types, because the type of streams in Copilot is not that big. It's also all the manipulation functions that come with it. Like suddenly there's a lot of duplication that goes away. There's a few other things that I talk about in the paper that I'm struggling to understand if there's a solution in the paper for what you said, but I don't think there is. I think this thing that you mentioned in GAC is not something I have explored at all. So I need to check it out. Thanks. No, it's just when I saw that usability, it made me think about it again. Sometimes when you write these expressions, you end up with a few nested layers and so on. And the paper also discusses how to make it amenable and how to make it easy to work with. As I said, you can embed things into other trees, and it's not just variables. You can embed expressions in other languages. So if you have some sort of like scripting language, you could embed an expression inside another, and that is discussed in the paper. And I also show how to take that stream-based language and interpret it, like take it all the way to the interpretation, which is part of what Copilot does, and also compile it to C. Now it's a toy version of a compiler to C. I don't give you the whole thing, but it shows how it could be done. And then there's a discussion also on the implementation. And the paper was originally submitted as a Perl. So there's many, many examples of everything that we have discussed. And these are the 2 repos for the tools that I mentioned. And as I said, you're more than welcome to try them. The tools also happen to follow a very thorough software engineering process. And this is all open source. Like, I don't keep a private version of these things. So you can see how we are developing high assurance Haskell at NASA directly on the repo. And you can see everything, how it is filed and it progresses and so on, which, apart from the talk, is a cool like software engineering experience. Now, there's uses for other things. Now, in the original version of this paper that I submitted to ICFP and got rejected, I also discussed user interfaces. And for example, the maybe thing can be used to encode changes in a value or in a type, which means if you have a user interface and you want to minimize updates, you could internally keep, just propagate the values of the type that have changed and then only refresh those in the user interface. There may be other uses for a maybe there that I have not seen. At some point, I explored the idea of using the list polymorphic type. Because if you use lists, okay, it's weird, right? It's a bit strange. So if you use lists, let me put it here, then you end up with multiple A's, multiple streams, and multiple operations, and so on. For this type, it's a little bit strange, but for others, it's like it gives you parallelism, but it doesn't enforce a particular order in which you have to enroll the elements, if that makes some sense. So you know how in Haskell you can use, sorry, I said parallelism, non-determinism. You can use lists to represent non-determinism. If you do it that way, then suddenly you have kind of like more granular non-determinism, but it doesn't enforce you to extract the elements in a particular order. And I have yet to find, like I found a few examples of things that you could do with it, but I haven't found a concrete, solid use case for this. You could also use a continuation monad, and then you have pre-applied. You have, you have elements to which, if you provide a value of that type, they will give you a result. And I'm also exploring, and this is kind of connected to what was discussed earlier in the conference, the idea of adding some sort of constraints to the fields. It's not just that I give you multiple possible values, it's that I also tell you how that field could be constrained in some way. I confess that I don't know enough type theory to fully understand the details of what's going on behind this. I'll be happy to collaborate with people who do, if somebody wants to help me formalize it and understand it. And that is pretty much everything I came to say. I'd be also happy to hear, well, I'm happy to take questions and yeah. So apart from GHC, has anyone used this? And I know it's in the wild. There's a library called Barbies that helps you work with these things, which, by the way, I discovered after I wrote the paper. I didn't steal it from them. Yes?
Yes, so I've used it. That was your question.
Well, you've
Right.
used it.
So,
okay.
Yeah, but anybody else have a question or a comment?
I probably missed something, but it looked like you would need partially applied type synonyms to do this, don't you?
You would need partially applied types.
Not type synonyms, type families.
Okay. And hang on. I think yeah.
I thought that wasn't supported.
So if I understand your question correctly, and I think if you use a new type wrapper, then it works.
Okay.
And this is explained in the paper, actually. I have the paper open right here. And at some point, I had to do something like that for the exact same reason. Yeah, here. Boom. And I think it was for that reason.
Okay, thanks.
Yeah.
Thanks for a great talk. That was very clear. Thank you. I have to say, though, I disagree a little bit with the premise.
Okay.
In that, so in GHC really leans heavily on this design pattern.
Yeah.
Now I'm also alongside GHC working in OCaml. OCaml does not use this design pattern.
Okay.
I prefer the OCaml. In that it's repetitive. It means that we have multiple AST type definitions with like that just, there'll be 20 constructors in a row that are just identical between them. And then there's a few differences. And so it also means that there's a few traversals that have to happen over both, like to calculate the size of it or something like that. And that code has to be repeated. So that is annoying. But it's just easier to work with. It means that when you're looking at the definition of the AST of the type, you get exactly what's on your screen. You don't get like half on this screen, and then you have to look at the particular instantiation of your F somewhere else to figure out the other half.
Okay.
Right, because the constructors list sort of.
Okay.
So just one person's experience, but after living both of them somewhat heavily. If I were designing from scratch, I would not use this pattern.
I understand. Okay. Okay. Okay, then I'm done. Bye. Okay. But yeah. Now I was going to say one limitation that I found when I was trying to write very generic stuff is that you can't pattern match on the cases on the constructors anymore. And to write functions, you have to assume things about the F. In most cases, I had to make things like applicatives or something like that. So as I was writing functions, I wished I had more language support to work with them, but I didn't even know how to express what I needed.
I'm happy to show you the spot in GHC where we get around that. I mean, because GHC has the exact same problem, and so there's the singleton type that we have to pattern match against. It's a small pain. We don't have to do it very much, but it's another bit of friction around this.
Yep. I think there was a 1, 2. Yeah.
Hello. This is a comment more than a question. There is another pattern similar to this. So some people here may be familiar with recursion schemes.
With a what?
Recursion schemes. And so in recursion schemes, if you would show your tree, all the places where your tree is recursive, you would replace with a pattern, with a type variable. And so in that first constructor where you say streamF, I think you would just have a type variable, and you would have that be the last type parameter of the type constructor at the top.
Mm-hmm.
And then you apply a fix. You have to make this into a functor, and you apply fix.
Yep.
And when you have done that, now you have a tree. And you can, I forget exactly where you put it, but you put this modifying higher kinded type into that tree and accomplish the same thing.
Okay.
In yet another way.
Thanks.
I'm also going to make a comment, and that is that the appreciation of what's easy using this pattern or not, it depends heavily upon what tools you have available to navigate the code and to figure out the types of your expressions. So it's not a definitive answer, whatever experience we have today programming Haskell, I believe.
So did I get your question right, that you were responding to his point of having the issue with navigating the keeping both notions present when you're working with the tree? Is that what you were asking about?
Well, Richard was saying if I were to write compiler from scratch, I probably wouldn't use this design pattern. When I said that depends on the tooling you have available to program, on your IDE, on what information can it give you immediately when you point at the code and try to figure out how your variables are being instantiated.
Would you agree with that?
Yes. I mean, it's easy to agree with because. Sorry. It's. I mean, I agree with that, but it's an easy statement to agree with because there's no limit on how good the tool can be, right? So if the tool is absolutely amazing and sort of does everything for me, then yeah, of course that's great. But just knowing how something is instantiated, that by itself wouldn't yet be enough for me to want to adopt this. Me personally, but others, this is, I think, something where reasonable people can differ. It's just my opinion.
Well, there's another.
So this totally separately. So you mentioned lists.
Yes.
I have an idea of where it might be useful.
Please.
When you want like information to flow the wrong way. So one thing that we maybe think we want to have in Haskell for some time is type-directed name resolution. So if you had, let's say, multiple different types that all had a constructor named cons, right? You want a vec type and a list type and then maybe some others. So it would be very cool if we could use type information to figure out, like if you write cons in your code, it would be good to use type information to do that. Right now, all name resolution happens in a completely previous pass. But I could imagine an implementation that in that name resolution pass produces a list of possible meanings for it, which then get disambiguated in a later pass. And that might be a place that lists could be useful. I don't know. Certainly haven't tried it, but that strikes me as the right kind of thing. When a later pass is used to inform an earlier one, might be the right shape. The last thing I wanted to say was the GHC's design is based on a paper called Trees That Grow.
Yeah.
Okay, so as long as you have that.
I know the paper and it's mentioned and discussed in this work.
Okay, great.
Thank you.
I just, quite a few years ago now, Kent Dybvig and his collaborators at Indiana built something called the NanoPass compiler infrastructure, which really works only for Scheme, but it addresses the problem of a collection of related abstract syntax trees that carry different values and have different constructors. And it does a whole bunch of the sort of boilerplate things for you. And I and a few others have felt ever since that we desperately need something like this for the statically typed languages, the ML family, Haskell. So if there are any PhD students in the room who want to tackle a hard problem, think about that one.
Bit of a comment here. I think just an idea to get around the issue of like the difficulty in writing functions that apply to these things generally. What you might want to do is, if you know ahead of time like the series of different f's that you'd want to use, or the general type of it, you could make like a single type class that lists all of the general operations that you'd want to use over them, instead of relying on something like applicative or something.
Okay.
And then you can generically work over all the different possible f's that you care about. But I don't know, maybe that wouldn't be that extensible, but that's a thought.
Comments, questions? Oh yeah.
Yeah, I think I just comment a little bit on the usability and the pattern synonyms because that's something we have encountered in work. It's really for function programming. A lot of it's really just design the algebraic data type. We spend a lot of time fine tuning this. Usually, sort of once you have the right data design, the code just follows, right? But I think there's a tension in the way that it's like how want to elaborate this data will look like. Sometimes it's just like, oh, I want to match my mental model or my knowledge about this domain model. We have a very nested ADT, and the pattern matching becomes very verbose. And then we have to introduce pattern synonym to reduce the verboseness of our code. Yeah, that's kind of like, but the pattern synonym effectively flattens the tree. But when you look at the pattern synonym, it really just make the tree flat. So your code becomes easier to do, yeah. So that's kind of tension. This is not really, I just look at your slide. I think that's something I just want to share. There's a tension in terms of design, especially on the ADT part. Yeah.
What else?
I have a question for you. You said earlier that you were a user of Barbies.
No, I was a user of this pattern.
Oh, okay, cool. Okay, great.
Kind of overlapped with the mention of Barbies.
Yep.
All right. Thanks, Ivan.
Thanks, everyone.
So this concludes the first ACM SIGPlan workshop on functional software architecture. Looking by how crowded this is, I'll declare it as a success. I hope you liked it, and maybe we'll do this again.
Can we please thank Michael for organizing this?